Uma história que começou em 1963, com décadas dedicadas ao desenvolvimento de processos, produtos e embalagens. O Instituto de Tecnologia de Alimentos não mede esforços para se manter como referência no setor alimentício, não só no Brasil, como no mundo. Por entender a importância da inovação e segurança de alimentos, bebidas e embalagens para o consumidor, o ITAL pesquisa e presta assessoria técnica, visando a eficácia e padrões mínimos de qualidade. Além de estar atento aos diferentes perfis de consumidor, o Instituto atua sempre com ética e respeito ao meio ambiente, priorizando a análise crítica para acompanhar a evolução tecnológica e de mercado. As atividades do ITAL são divididas em 3 grandes áreas. A tecnologia é desenvolvida e aplicada nas unidades especializadas em carnes, cereais, chocolates, balas, confeitos, produtos de panificação, laticínios, frutas, hortaliças e engenharias de processo. A ciência e a qualidade são prioridades dos laboratórios de análises químicas, físicas, sensoriais e microbiológicas. A embalagem é o foco dos setores especializados em materiais metálicos, vidros, plásticos, celulósicos e para distribuição e transporte. E o conhecimento vai além dos muros da instituição através de artigos, publicações e eventos. O ITAL valoriza as pessoas que são força de trabalho e razão de existência. Por isso, está presente em importantes programas de governo que abrangem todas as classes e diferentes gerações. São décadas de constante reinvenção, aprendendo e ensinando, décadas de reconhecimento com a bagagem do passado e a modernidade do presente. Com funcionários qualificados, clientes, parceiros e fundações de apoio, o ITAL tornou-se fundamental no setor de alimentos, bebidas e embalagens.
O FORC é um centro de pessoas, que é um centro que agrega pessoas que trabalham, que desenvolvem pesquisa aplicada em diversos pontos da ciência do alimento e da nutrição.
Já se pensava em fazer um centro de alimentos dentro da USP. E a gente achava que a USP, se ela unisse todos os fragmentos, todos os grupos que trabalham com alimentos numa única coisa, nós ficaríamos invencíveis.
Por que não? Por que não fazemos esse projeto, né? E aí nós começamos a conversar e foi um longo processo, porque foram 2 anos para a FAPESP decidir que nós tínhamos expertise suficiente para ter um centro.
A ciência do alimento, a ciência da nutrição, ela é multidisciplinar por definição. Então eu costumo brincar sempre que o mundo tem 9 bilhões de especialistas em ciência de alimentos. Todo mundo entende de alimentos, porque todo mundo come. Existe uma frase famosa do Luiz Fernando Veríssimo: o poder acaba, a visão acaba, o sexo acaba, mas a fome continua.
Uma das coisas que a gente realmente mostrou é que esse tema tem uma importância capital para o país. 30%, quase 40% do nosso PIB vem justamente desse setor, do setor da agricultura, do setor de alimentos. E isso daí tem um reflexo direto, nutrição, para a população.
Nós podemos, em parceria com a indústria, desenvolver projetos que sejam cientificamente de alto padrão, aplicáveis para a indústria que beneficia a sociedade.
A pós-graduação é importantíssima porque a maior parte justamente de toda a pesquisa que é feita, ela é feita no laboratório por pós-graduandos. Quer dizer, os mestrandos e doutorandos, eles formam a maior parte, vamos dizer assim, dos nossos recursos humanos. Um recurso humano altamente especializado.
Hoje nós temos no FORC 30 jovens pesquisadores trabalhando com a gente e nós conseguimos chamar inclusive pesquisadores do exterior.
A gente percebe que existe um avanço considerável em quantidade e em qualidade também.
Uma das coisas que também a gente quer muito é que a gente tenha essa parceria com universidades e institutos de pesquisa mundiais. que trabalhem com alimentos e nutrição. E isso está acontecendo de maneira bem forte.
Se vier uma indústria aqui dizendo que quer desenvolver alguma coisa, quer aprofundar um determinado tema, nós temos as competências aqui para ajudar.
Dentro de uma universidade, dentro de um laboratório, você tem a condição de trazer aquilo lá, aquela ideia, tornar ela realidade. E por isso que nós somos apaixonados pelo nosso trabalho.
Eu acho que inovação é quando você vê alguma coisa de um jeito diferente do que os outros veem.
Nós criamos lá embaixo um laboratório que é de primeiríssimo mundo e a gente consegue fazer pesquisas de altíssima qualidade.
Essa é a nossa pretensão, que a gente tenha um centro de pesquisas dentro da Universidade de São Paulo que seja independente.
Consolidar o grupo e ir para frente daí. Se tornar uma referência dentro do universo de alimentos e nutrição para o país e para o mundo.
Nós queremos continuar formando gente muito boa, mas nós queremos formar gente muito boa e produzir ciência muito boa. E como é que a ciência é muito boa? A ciência do 1970 não serve mais. A ciência do 2017 hoje ela é toda integrada, ela é toda colaborativa, ela é toda multidisciplinar, ela é toda sinérgica. O nosso centro ele está no momento certo funcionando dessa forma.
Olha, aquilo que está na nossa missão, viu? Ciência para melhorar a vida.
Good afternoon, everyone online. Good morning, good afternoon, good evening, even if you're in a time zone where it's evening or getting to evening. Welcome to the second day of the LESS Icmsf webinar. We are starting session 3, and your moderators are Marcel Zwietering, who is the Icmsf chairman, and myself, Leon Gorres. I'm the Icmsf secretary. We especially want to thank the sponsors, the Institute of Food Technology, the Food Research Center, and Merck for their generous support to our webinar. And we'll start the proceedings right away, having a look at the schedule ahead of us. So we're starting session 3, which is on microbiological criteria. Yesterday, we heard in the first sessions about useful microbiological testing. We learned about microbiological criteria that are used for lot acceptance, the acceptance of batches of food, where the stringency of the tests are targeted at the risk that microorganisms may pose to consumer safety, or where they have a relevance with process control. Today, we will look at further aspects of microbiological criteria, especially the underlying statistics. And I know that statistics is not everybody's favorite topic, but it's good to be aware of some of the key principles underlying useful testing, microbiological testing of food, for food safety or for process control. So the first 3 presentations of today will zoom into that statistics topic. The 4th presentation will introduce you to the Icmsf sampling plan tool, which is an Excel-based tool that may help you to calculate the performance of different sampling plans. That helps you also then to understand what is the stringency of a sampling plan, and maybe can I get a different view on parameters, a different set of parameters with the same stringency. We are going to use, like yesterday, the Icmsf video clips. Marcel and I will introduce them, and you will try to give you a summary of what we think the highlights of every presentation are, the take-home messages of every presentation are. You can find these Icmsf video clips as well on the Icmsf website. We have a tab called Videos, and under it you see some of the videos related to our presentations around the world, for instance at IFB or last year's webinar. But under this tab you also will find playlists about that contain these video clips. We have 2 playlists. One we made in 2017 Some of the video clips that we showed yesterday were from this list, but there's also a list that we made in 2020. Marcel and I contributed that additional playlist. And next to the video recordings, you can find on the website as well the PDFs. So you can find the slides as well that we use in those playlists. So for today, we'll start with a presentation by Marcel on microbiological testing and the distribution of microorganisms. Marcel is with Wageningen University and has been an Icmsf member since 2005, and he's the current chairman of Icmsf, as I mentioned before. And Marcel will explain to us the way that microorganisms are distributed in food, and that is key information for us to build useful testing approaches. Thiago, could you start, please, the first video?
This presentation explains statistics related to microbial sampling plans. My name is Marcel Swietering and I'm Professor of Food Microbiology at Wageningen University. I'm a member of the Icmsf since 2005. Stochastic processes are known from the casino, where gamblers decide where to place their bet. Believe it or not, statistics are also involved in testing food products. In order to have a good foundation for food safety, you definitely need more than only sampling. You see here a building that lasted for ages because of the solid foundation. And also for food safety systems, they should be really based on several levels of foundation. You first need your prerequisite programs like GMP and good hygiene. Then you need a good HACCP plan. You need to validate your CCPs, and then you are going to monitor your critical limits. And if you have done that all, finally, you're going to verify the adequacy of your sampling plan of your program by using microbiological criteria. If your system is only based on the last part, we're going back to the foundation of a house of cards. Only testing by microbiological criteria is not a good basis for your food safety system. Sometimes a microbiological criterion is described as absence of salmonella. Is that a well-defined sampling plan? No. On this slide, you see a sampling plan for powdered infant formula for Chronobacter and Salmonella. And in this sampling plan, you have to take 30 samples of sample weight 10 gram for Chronobacter and 60 samples of sample weight 25 grams for Salmonella. And C equals 0, meaning that no sample is allowed to give a positive result. It is important that all these three aspects are described: the number of samples N, the C value, and the sample weight. The standard method to perform the analysis must be prescribed because different methods may also yield different results. In the Codex Hygiene Code for PIF hygiene criteria are also described for mesophiles and Enterobacteriaceae. And here you see two important differences from the safety criteria. First of all, you see now that the C value are both equal to 2. So 2 of the samples are allowed to be positive. For Enterobacteriaceae, the test remains a qualitative test, a presence-absent test in 10 gram. But for mesophiles, a quantitative test is used, so the microbiological limit is a concentration. In this case, it's a 3-class sampling plan with a lower limit small m and a higher limit big M. None of the 5 samples are allowed to be above the 5,000 per gram. 2 samples are allowed to be between 500 and 5,000, and the others have to be below 500. Testing a certain number of samples with a low level of contamination can be compared to a lottery. And here you can see 2 results of the one time with 5 negatives and one time 5 samples with 1 positive. This gives, of course, the illusion that the first batch is free of the pathogen and the second is contaminated. However, since sampling is a stochastic process, it could also be another situation. It could be that in both cases there is a very low and equal level contamination, and in the second case you got lucky and hit a positive sample, while in the first batch you didn't. And as a joke, you could even say that in the case of the positive found, the batch is now safer since at least you took out one of the pathogens from the below batch. So a positive means something, but a negative is definitely not a guarantee. It is a misconception to think that if all your samples are negative, that this is a proof that your batch is free of the pathogen. It only proves that the samples you tested are free of the pathogen. All these aspects are described in a paper in Annual Reviews in Food Science and Technology, where we looked at all kinds of distributions of microorganisms and looked at the homogeneous and heterogeneously distributed organisms and looked at presence-absent testing and quantitative testing. But I will start with the homogeneous contamination. But later we will also look at the heterogeneous high-level contamination and a heterogeneous low-level contamination. And in this paper, we also look at localized high-level contamination, localized low-level contamination. But for now, we will only describe A, B, and C. And in this clip, only A, the homogeneous contamination. So if we have a homogeneous contamination, which results from an ideally mixed product like a liquid, the organism will be randomly spread, and we can look at what the performance of the sampling plan will be. On the left side, you see the prevalence of the organism in a sample, so the probability to have a defective sample. And in the next column, you see the probability to accept the batch if you would take only one sample. The probability that no contamination is found logically equals 1 minus p defective. So if a sample has a 5% probability to contain the organism, I have 95% probability to not find the organism in one sample. So to improve the performance, we often take more samples to be more sure. For example, if we take 2 samples, then we have to put this 1 minus p def to the power 2, since the first sample needs to be negative and also the second sample needs to be negative to have no positive samples in total. And for 5 samples, we have to do that to the power 5. And for 30 samples, we have to do that to the power 30. So the more samples you take, the more likely you are to detect the higher defective rates. However, even at 30 samples, the probability to detect a 1% defective rate remains rather unsatisfactory. You have still 26% probability to miss that contamination level, and if this is a serious pathogen, of course you do not want to send that batch with hundreds of thousand products to the market with a 1% defective rate. Often a 1% defective rate is not acceptable, and even a sampling plan with 30 samples has a rather high probability to miss this. So to conclude, if all samples in the sampling plan are negative, this is not a guarantee of absence in the whole batch. On the other hand, if a positive sample, that does indicate presence in the lot. Thus, while sampling and testing does not provide definite proof of absence in the whole batch, it is useful for finding big deviations and highly contaminated lots. And it's also useful to verify overall control of food safety. Further information and tools can be found on the Icmsf website.
Leon?
Marcel, that's not the screen that I wanted to show.
Can you show? I should not show. Or...
Well, you are showing. Oh, sorry. Sorry for that. Should be on my screen again now.
I thought you were sharing. Yeah.
Yes, I was, but maybe a hiccup, a technical hiccup. Sorry for that. So Marcel presented on the distribution of microorganisms in food, and that's very important information. We know that testing alone could be considered a lottery. Marcel compared it to a casino situation where there's a chance to find organisms or not. And yesterday we discussed that end product testing, environmental testing are very important as part of the total food safety management system. Marcel compared that to the to the pyramid that you can make out of different parts of a food safety management system. For verification, for validation, testing is very important. And that's why we really need to understand the principles of how microorganisms are distributed in food lots, because knowing their distribution, we can see how we can best simulate the distribution, how we can best analyze and statistically test for them. And also because it helps us to understand what organisms to target for when we design tests and when we do tests for validation or verification purposes. So then we are at the next video clip, which will be introduced by Marcel.
So the next video clip will be given by Martin Kool, and it will be about operating characteristic curves. So we have just seen if contamination is homogeneously distributed in a well-mixed fluid, for instance, but in many cases, there will be not a homogeneous distribution. And then we can also look at how well the statistics work and what is operation characteristic curve, how performant or sampling plan will be. Can we go to the next slide, Leon? Yeah. So Martin Kool was formerly the chairman of the Icmsf. I succeeded Martin, and he before also worked at the CSIRO in Australia, but currently he's with Wine Australia. And he will explain the sampling plan performance, but also with a non-homogeneously distributed microbial contamination. Thiago, can you start the video, please?
Hi, I'm Martin Kool, and I'm the Science Director for Agriculture and Food at Australia's National Science Agency, the CSIRO, and I'm the current chair of the International Commission on the Microbiological Specifications for Food, or Icmsf. And it's a pleasure to spend a few minutes with you today to explain the statistical basis of sampling plan, operational characteristic curves, and how the performance of a sampling plan can be related to the level of a hazard controlled and to other risk management metrics such as food safety objectives. The operating characteristic curve describes the probability of accepting a lot for a given sampling plan against the proportion of lots that are defective. The slope of the curve gets steeper the more samples that are taken, and here we're taking 2 or n is 2, 5 or 10 samples. In other words, the sampling plan gets more stringent the more samples we take, and the lower the probability is that we will accept a lot, even if it is unsuitable for a given proportion that's defective. Taking a sample is very much like tossing a coin in the air, where the result can be heads or tails. In sampling, the results can be presence or absence of a pathogen, and so the operating characteristic curve can therefore be constructed based on simple probability statistics. And in the next few slides, I'll just take you through how this works in a series of pictures. So the diagram along the bottom represents 10 lots of foods with a different proportion of defects shown as the red dots, from none out of 10 on the left-hand side, all the way to all of them being defective, or 10 out of 10 red dots on the right. So in this first example, if we take no samples, then the probability of accepting a defective lot is 1, or 100%. If we take one sample, then the probability of accepting the lot is exactly proportional to the proportion that is defective. So if there's 1 out of 10 defective, or 0.1 proportion defective, then the probability of accepting that lot is 0.9, or 90%. As the proportion increases to 0.2, then the probability is 0.8, or 80%, 0.3, 70%, and so on and so forth. Okay, so let's take a look then if we take 2 samples. Using our example of 1 out of 10 defective, or 0.1 defective, if we take 2 samples, each time we take a sample, it has the same chance of being accepted at 90%, or 0.9 probability. So the probability of accepting the lot, if we take 2 samples, is just a product of this. So in other words, 0.9 times 0.9, which gives us 0.81. Now the same principle applies if we take 3 samples, then it's just 0.9 times 0.9 times 0.9, or 0.73. And this is how the slope of the curve increases as we take more and more samples. Now, eventually, when we take so many samples, in this case 30 samples, we start to approach what we term as the idealized situation. This is where, as soon as even 1 out of the 10 is defective, then we have an extremely low probability that the lot will be accepted. So hopefully this has helped to demystify a little bit operating characteristic curves and to show you that really they're just based on simple probability statistics. What I'd like to do now is to move on to how we can relate the performance of a sampling plan to the level of a hazard that is controlled. Now, in the normal way that we express the performance of sampling plans in a table, for a lot which is 2% defective, even when we take 60 samples, we still have a 0.3 probability or 30% chance that we'll accept the lot even if it's defective, in this case 2%. Now, the main problem of describing the performance of a sampling plan in this way is that as a microbiologist, I would like to be able to understand the performance of a sampling plan in terms of the level or concentration of a pathogen that could be detected by a given plan, which is really much more meaningful in terms of risk. Also, we want to be able to express the performance of a given plan to other risk management metrics, such as food safety objectives, which is the level of a hazard at the point of consumption that achieves the appropriate level of protection. So the issue is, how could we relate the performance of presence or absence testing and a sampling plan to the level or concentration of a hazard that would be detected with a given chance or probability? And this is the approach we used. First, in most cases, the distribution of counts of microorganisms are usually skewed and can usually be expressed as a log normal distribution. And if the food is well mixed and reasonably homogeneous, then the distribution will be tighter and have a lower standard deviation. Second, based on the log normal distribution, we can determine the proportion defective for a given mean count. And then third, using the operating characteristic curve, we can relate the mean count to the probability of acceptance. And what I thought I'd do is to try and illustrate this visually with a series of animations. So here's a plot which now relates the probability defective against a log colony forming units per gram scale. And for the purpose of this, we're going to have a limit of 3 or 1,000 colony units per gram. Now, if the mean concentration of counts is down here, say at 1 log CFU or 10 per gram, then the whole of the curve is on this side and there are no defectives. But as we increase the mean count and move the distribution to the right, then we start to increase the proportion that's defective until eventually all of the samples are defective. So we can now plot out the proportion defective for a given mean count. So here we are, we're just moving the distribution to the right-hand side, and we can now build a curve relating proportion defective to the mean count. So far so good, but we're interested in relating the probability of accepting a lot in relation to the mean count. But based on the operating characteristic curve that I've talked about earlier, for a given proportion defective, we can calculate the probability of acceptance. So for each proportion defective, we can now convert that to the probability of acceptance, and then link that to the mean concentration, which is what we're interested in. So now we can relate the performance of sampling plans to the mean concentration of microorganisms that could be detected at a given probability. So what can we do with that? Well, here's an example from the Icmsf cases, but now we have the increasing stringency from the top left of the cases to the bottom right. We can also see now in this in terms of the mean concentration of organisms that would be detected with a 95% probability. Now, if you'd like to know more about this work, you can find a lot of the principles described in the following papers. And also, fortunately, to make it easier, the Icmsf has created a web spreadsheet tool that does all of the calculations for you, and this can be downloaded on the Icmsf webpage. So, to conclude, operating characteristic curves are based on simple probability statistics, can be used to determine the probability that a lot will be accepted for a given proportion defective. The Icmsf has developed a new approach that relates the performance of the sampling plan to the level of hazard that can be detected. Finally, this is important because it relates it to other risk management metrics and supports the use of microbiological criteria and testing in the verification that a food safety objective has been achieved. Thank you.
Okay, so in this lecture, Martin Kool did explain further on the performance of sampling plans. So it wasn't going also from the probability if you have a certain number of samples, but then also including the distribution of the contamination. And the parameters of the sampling plan, the number of samples that is allowed to be positive, the C, they all determine the probability of accepting a defective lot. And it's important to realize always there is a sample that you measure, and then based on the number of samples, you also have a probability to accept a lot depending on the results found and the C value of your sampling plan. And the operating characteristic curve links the probability of the acceptance of the lot to the level of the defectives in the lot. And of course, the higher the risk for the consumer, so the presence of a pathogen or the loss of control of the operation, the less likely the acceptance of the lot with the defectives. And that is how, as it should be. The more dangerous the batch is, the higher the probability that you will reject the batch. But still, there is always a little bit of lottery involved. It's not black and white. We don't get those operating characteristics curves exactly parallel, but the more samples that we do take, the better the information gets. So we see already some questions coming in, so thank you for that. That's very good. We'll keep on sending questions that we can then treat later on in the Q&A, but I now give the floor again to Leon to introduce the next clip.
Thank you very much, Marcel, and the next clip has been made by yourself, and that is about why do we have so many different types of sampling plans. Yesterday we already mentioned there are 2-class plans, 3-class plans. You have some plans that are qualitative, others are quantitative. They're targeting different microorganisms. So people may be confused and wonder indeed why we do have so many different types of sampling plans. So let's go and look at Marcel's video clip. Thank you, Thiago, for starting it.
Many different types of sampling plans exist. Why is this the case and how to handle them? My name is Marcel Swietering and I'm Professor of Food Microbiology at Wageningen University and member of the Icmsf since 2005. We do have different types of sampling plans, since the world is not black and white, and neither microbiology is black and white. If we measure microorganisms, they can be indicators, so not per se dangerous organisms. We do have organisms that can produce toxins, but only if they are at a very high level. On the other hand, infective microorganisms might already make you ill at low levels. Also, not all humans are the same. Infants and people in hospital, specific target groups can be more vulnerable. It also depends where in the food chain we measure and what happens after the sampling point. Will the organism be inactivated or can they even increase in numbers after the sampling point? We can measure, for example, the total plate count. All aerobic organisms then will be counted, which is an indicator for the microbial levels, but not per se indicating danger, but for instance spoilage. Also, mesophiles indicate organisms that can grow at moderate temperatures, but often are not pathogenic. Enterobacteriaceae are typical indicators of hygiene. Bacillus cereus is an organism that at higher levels can cause problems in humans. Campylobacter and Salmonella are infective organisms that even at a rather low level have a pertinent probability of infection. Poultry is however not eaten raw and levels are expected to go down before consumption. If the Salmonella is present in a ready-to-eat food, it's more of a risk, even more so if it would be in food for infants, like powdered infant formula. There are many different situations to assess the microbial status, so we need many types of criteria. we have qualitative and quantitative tests. In qualitative tests, we enrich a sample and determine if there is at least one cultivable cell in a sample. In a quantitative test, we really count the number of cells present. We do have 2-class and 3-class sampling plans. And we can use them as food safety criteria or as process hygiene criteria. When a food hygiene criterion is not complied with, appropriate management actions have to be taken, while if a food safety criterion is surpassed, a food should not be on the market. A qualitative test is testing for presence or absence, or detected, not detected. Here the amount is investigated, for example 10 grams of 25 grams, and that clearly needs to be stipulated. A quantitative test determines if the concentration is either below or above a certain level, for example 100 colony forming units per gram or CFU per gram. Then we have 2-class and 3-class plans. A presence-absence test is clearly a 2-class because it's detected or not detected. Also below or above 100 CFU per gram is a 2-class plan. For a 3-class plan we have two limits separating the 3 classes, for example, which is limit 500 and 5000. We have as classes smaller than 500, between 500 and 5000 and above 5000. An example of a qualitative 2-class plan is the Codex plan for Salmonella in powdered infant formula. 60 samples of 25 grams need to be tested for presence of Salmonella. An example of a quantitative 2-class plan is the Codex plan for Listeria monocytogenes in food not supporting growth with 5 samples below 100 CFU per gram. These two are food safety criteria, focusing on pathogens in a ready-to-eat food. Indicator organisms may be used as process hygiene indicator and are often defined as 3-class plan. An example of a quantitative 3-class plan is the Codex plan for mesophiles in powdered infant formula, having as two limits separating these 3 classes, 500 and 5000 CFU per gram. Here both limits are quantitative. But one could also consider to have the lower level M as a qualitative and the upper level big M as a quantitative test, being a 3-class mixed sampling plan. The lower limit M can then be not detected in 25 grams and the upper limit M 100 CFU per gram. The Icmsf spreadsheet has various steps for the different types of sampling plans. 2-class enrichment for the 2-class qualitative criteria, 2-class counts for the 2-class quantitative criteria, 3-class counts for the 3-class quantitative criteria, and 3-class mixed for the 3-class plan with a lower qualitative limit and a higher quantitative limit. Here you see the Codex sampling plan for PIF. This is a quantitative 2-class plan. It only has detected or not detected per sample of 25 grams, so it's a 2-class and it's qualitative. The 2-class enrichment is the tab to choose. Now you see the Codex plan for Enterobacteriaceae in PIF. This is also a qualitative 2-class plan. It only has detected or not detected per sample, so it is a 2-class plan and it's qualitative. 2 of the enriched samples of the 10 gram are allowed to be positive for the criterion to be complied with. Again, the 2-class enrichment is the tab to choose. In the Codex plan for Listeria monocytogenes in RTE foods that do not support its growth, a quantitative limit is given of 100 CFU per gram. Here the 2-class count is the tab to choose. Also in the EU plan for Campylobacter in broilers, a quantitative limit is given of 1000 CFU per gram. This is a quantitative plan and it has 2 classes. 15 of the samples are allowed to be positive. Here again the 2-class count is the tab to choose. The number of samples allowed to be positive changed over time from originally 20 in 2018, then to 15 in 2020, and from 2025 it will go to 10. In the Codex plan for mesophiles and PIF, also quantitative limits are given. This is a quantitative plan and it has 3 classes, below 500, between 500 and 5000, and above 5000. 2 of the samples are allowed to be between 500 and 5000. Here the tree class count is the tab to choose. In a tree class mixed plan, the lower limit of the tree classes M is a presence-absence test. The upper limit, big M, is a quantitative test. Here the tree class mixed tab needs to be chosen. This plan detects a high prevalence since more than one of the enrichment 10 will be positive. It also can detect a lower prevalence, high concentration by testing whether occasional positive samples are larger than 100 CFU per gram. Sampling plans can give information for producers and for food safety authorities. This information can be targeted at safety, hygiene or spoilage, and the testing can be performed at different locations in the food chain. Since different targets are needed for these different aspects, different types of sampling plans do exist, like 2-class and 3-class plans and qualitative and quantitative tests. In this manner, microbiological criteria can, together with other measures within food safety management systems, give confidence that processes are under control.
Great, thank you for that presentation, Marcel, your virtual self. So it's clear that sampling plants are there because they serve a specific purpose: end product testing, process control, and they target specific microorganisms and groups. In a way, they are set up to have a certain stringency because that relates to the risk that they are set to control. Qualitative and quantitative tests together give us a big range of the depth in which we can go into finding microorganisms, the lower levels that we can qualitatively find them or quantify them. So that all fits together with our ambition to really find organisms and then quantify them in relationship to whether we accept batches, whether we are in control of process, and all related to acceptable risk. And in that regard, acceptable risk can vary around the world, as we had seen in our discussions yesterday. But yes, there are many different sampling plan approaches. There are many different microcriteria, but they serve a purpose, and that purpose is useful if the criteria are set right. So the next presentation will be introduced by Marcel.
Yeah, and I will introduce the next one because the clip has been prepared by Leon. And Leon will explain how now the Icmsf sampling plan tool can be used to look at the performance of these different microbiological criteria. In the former clip, I explained that there are all kinds of different criteria for all kinds of different situations of lower risk or higher risk. But how can now the Icmsf sampling plan tool be used to look at the performance of such a plan? Next slide, please. Oh, yeah, this one. So the presentation will be given by Leon, and he will explain how this can be used, and he specifically will use an example from the Codex Microbiological Criterion for Listeria in ready-to-eat foods. Please, Thiago, can you start the clip?
Hello, my name is Leon Gurris. I'm a food safety expert residing in the Netherlands, and have worked in the area of food safety research for government and industry. Since 2001, I've been a member of the International Commission on Microbiological Specifications for Foods, or Icmsf, and I represent the Commission at Codex Alimentarius. This presentation is one of several Icmsf video clips on the use of the Icmsf sampling plan tool. These are meant to help users understand the performance of sampling plans specified in microbiological criteria, abbreviated as MCs or as microcriteria. In this one, I will introduce you to the MCs that Codex Alimentarius has proposed for Listeria monocytogenes in ready-to-eat foods. Attend other clips in this series to learn how our Icmsf sampling plan tool can actually be used to assess and interpret the performance of these MCs. As you may know, Codex Alimentarius is the global intergovernmental body that develops food safety standards, codes of practice, and guidelines. When national governments choose to implement elements of these in their regulations as microbiological standards, these are mandatory to comply to for the industry that it concerns. Sometimes there are multiple MCs included in a single standard. In this video clip, as said, I would like to explain to you how the Icmsf sampling plan tool can be used to investigate the performance of such MCs. Understanding the performance of MCs is important for food industry and other stakeholders in the context of the compliance of food products to microbiological standards. The microbiological criteria that I will discuss are the ones that Codex proposed for Listeria monocytogenes in ready-to-eat foods. I will first introduce you to the Codex guidelines in which these MCs are included. Then I will show you details of the MCs proposed for two different groups of ready-to-eat foods. Finally, I will compare the performance of these two MCs to illustrate that they are intended to make the control of Listeria monocytogenes proportional to the potential consumer risk. First then, to the Codex guideline. It's labeled CAC/GL 61-2007. The guideline is entitled Guidelines on the Application of General Principles of Food Hygiene to the Control of Listeria monocytogenes in Foods. It has been issued firstly by Codex in 2007. This guidelines document concerns all types of food, but for this presentation we are actually especially interested in those foods for which Codex has established that the use of microcriteria may help governments and food industry to control the occurrence of Listeria monocytogenes and thus to protect consumers. The foods for which Codex believes that MCs are useful are the so-called ready-to-eat foods. These are foods that are literally eaten by consumers as they purchase them. So between purchase and consumption, these foods are not handled or treated in such a way that any risk to consumers is effectively mitigated. For instance, these foods are not subjected to a heat treatment that would kill or inactivate all cells of the pathogen. The Codex code has several annexes. Full details of the rationale for establishing MCs for some food groups can be found in Annex 2 of this guideline. I believe it makes for an interesting read. The two MCs that we will look at a little bit later in this presentation are also included in this Annex 2. But first, a few words on microbiological criteria and how the sampling plan fits into the concept. The use of the concept of microbiological criteria to control microorganisms in a risk-based way has been developed by Icmsf in the 80s. Codex Alimentarius adopted and evolved the concept through several of its standards, codes and guidelines. For instance, through Codex Code CXG 21, issued first in 1997 and updated in 2013, Codex informs governments and industry on the best practice for setting and using MCs. Note that there are many components included in the MC concept according to Codex. It's a long list. It's the food, process or control system to which the MC applies, the point in the food chain where it applies, the microorganism and why it has been selected, the microbiological limits, small m and big M, and the sampling plan defining the number of sample units to be taken, N, the size of the analytical unit, and the acceptance number, C. An indication of the statistical performance of the sampling plan, analytical methods and actions to be taken when the criterion is not met. With all these components specified, it is expected that an MC is absolutely clear to stakeholders. In order to obtain information relevant for establishing useful and proportional MCs for the pathogen and commodity combination we are discussing, Codex Alimentarius commissioned a microbiological risk assessment, or MRA, concerning Listeria monocytogenes in RTE foods. This MRA was compiled by experts working under the umbrella of the Joint Expert Meetings on Microbiological Risk Assessment, GEMRA. The GEMRA group published their investigation and findings in Book 4 and 5 of the series of GEMRA reports. In their risk assessment, the GEMRA group investigated 4 types of RTE foods in great detail. In pairs, these 4 types are considered as representative of the range of RTE foods on the market. Pasteurized milk and ice cream both are pasteurized products in which LM levels are typically low. But milk supports the growth of the pathogen and it is consumed a lot. When properly frozen, ice cream doesn't support the growth of LM. Fermented meat and cold smoked fish are infrequently consumed but frequently contaminated with LM. While fermented meat does not support growth of the pathogen, cold smoked fish does. The findings of the GEMRA experts can be summarized in the following 3 key insights that are relevant for establishing microcriteria. Number 1, the vast majority of illnesses due to Listeria monocytogenes, i.e. listeriosis cases, results from the ingestion of very high numbers of cells of the pathogen, in the order of millions per gram. 2, when generally healthy people consume RTE food with low numbers of LM, there is a very low probability of illness. And 3, RTE foods differ in 2 important aspects: the relative presence of LM and the ability of the food product to support growth of the pathogen. The latter key difference was considered by Codex to be a good basis for the control of LM and for the protection of the health of consumers. That is why Codex included 2 MCs in Annex 2. 1 MC for foods in which growth of Listeria monocytogenes will not occur, so foods that do not support LM growth, and another MC for foods in which growth of L. monocytogenes can occur. Those are the foods that do support LM growth. Here you see an overview of the MC proposed by Codex for RTE foods that do not support LM growth. The top part, the data in the box, is what often is included in microbiological standards. But here you also see all the other details that Codex considers important too. Codex specifies that the food criterion applies to Codex specifies the type of food that the MC applies to, namely the RTE foods that do not support LM growth. The microorganism is clearly identified, L. monocytogenes, and it is stated that the MC applies from the end of manufacture or port of entry to the point of sale. The sampling plan and limit for LM are specified, as well as details of the method for detection, and the typical actions to take when a food lot does not meet the MC. To help stakeholders with the interpretation of the stringency of this MC, the performance of the sampling plan is noted as the geometric mean concentration of LM counts given certain assumptions. These assumptions are that pathogen counts in the food lot are log normally distributed, that the analytical standard deviation is 0.25 log CFU per gram, and that the confidence to detect non-compliant lots is 95%. This MC has been established on the basis of some of the key findings from the GEMRA report, which are paraphrased on the top of this slide in terms of rationale. For foods not supporting LM growth, a low level of the pathogen may be tolerable for the generally healthy consumers, while high LM levels that are unsafe for these consumers occur very, very infrequently. Moreover, levels of LM found in RTE foods are very rarely over 1000 CFU per gram. On the basis of these insights, Codex proposed a 2-class sampling plan for LM, in which the limit m is 100 CFU per gram. The number of sample units to test, n, is 5, and none of these, c is 0, should be over the limit of m. The food lot would not be compliant when 1 or more of the 5 sample units would be over 100 CFU per gram. Assuming a log normal distribution of counts, a standard deviation of counts of 0.25 log CFU per gram and 95% confidence to detect a non-compliant lot, the interpretation of this MC for the status of the food lot that just meets the sampling plan is specified here. For such a food lot, it would be expected that LM levels in 55% of samples taken would be below 100 CFU per gram. But note that 100 CFU per gram is not an upper limit for LM, because 45% of samples would be expected to be over 100 CFU per gram. However, of the samples over 100 CFU per gram, only a small fraction, 0.002, would be expected to be over 1000 CFU per gram. Here you see the MC that has been proposed by Codex for RTE food in which LM can grow, so foods that do support LM growth. Again, all necessary details are specified to make the MC clear to stakeholders: the pathogen, the food type and point of application, the sampling plan and limits for LM, details of the method for detection, and the typical actions to take when a food lot doesn't meet the MC. Also in this case, the performance of the sampling plan is specified, given the same assumptions as we saw for the other MC. Concerning the rationale for this MC, a basic insight is that there is no control of the growth of LM when it is present in the food, and that therefore an MC should help ensure that LM levels in a food lot are so low that there is a rather large safety margin to those levels that are considered unsafe. Codex considers that an MC with a two-class sampling plan, N is 5, C is 0, and M is absence in 25 gram, meets that requirement. Note that absence of LM in 25 gram in combination with the method of LM detection advised by Codex, which is the ISO 16140, means that the LM concentration in a sample unit would be less than 0.04 CFU per gram. Given these assumptions, a food lot that would only just meet the sampling plan is as specified here. It is expected that 55% would be negative for LM, while 45% would be positive. Of the positive samples, 0.5% could be above 0.1 CFU per gram, but even much smaller fractions would be above 1 or 10 CFU per gram. In this slide, I place the MCs for the two groups of RTE food products side by side to compare their stringency of control over LM. The left plot indicates the distribution of LM counts in a lot of food supporting growth of LM, and the right plot is for a lot of food that does not support LM growth. As you can see, the geometric mean for the food lot supporting growth is between 3 and 4 logs lower, in part providing for what was thought by Codex to be a necessary safety margin. So while both MCs should not be considered as lines in the sand, they do provide for a risk-based and proportional stringency of control on the occurrence of LM in RTE foods. In summary, Codex Alimentarius typically uses risk assessments to inform its risk management decision-making. The microcriteria that Codex established in this way for the control of Listeria monocytogenes in ready-to-eat foods are risk-based. On the basis of the micro-risk assessment carried out by GEMRA, Codex has proposed separate MCs for foods that do and for foods that do not support growth. The stringencies of these separate MCs regarding LM control are proportional to the consumer risk potentially associated to these two different groups of RTE foods. Please see our other clips concerning this Codex guideline and how the Icmsf sampling plan tool can actually be used to assess and interpret the performance of the two MCs. For more information on Icmsf, you're welcome to visit our website, icmsf.org. I thank you for your attention.
So you have seen in the presentation of Leon how different organizations can set recommendations, like for instance the Codex Alimentarius, but also of course national governments or other organizations can set microbiological criteria. And given those criteria, we can determine a certain sampling plan performance. And that sampling plan performance should of course be related to the risk that we would like to accept in a certain food. And the Icmsf sampling plan tool can be used to determine the performance of these plants. And as Leon showed clearly in this presentation, the difference of performance of the sampling plan for foods that do support growth and sampling plans that do not support the growth of food. And there was a very large difference between the batches that are accepted with these two different sampling plans. But still, stochasticity is involved in that. It's not black and white. There is a certain probability, even for the growth sampling plan, that you sometimes detect a sample that you rather would not send to the market. But there is a very large deviation between the two, and the performance of the sampling plan for products that do support the growth is much more stringent. And the stringency underlying these criteria are often based on microbiological risk assessment and risk management. So depending on the severity of the risk, on the probability of the risk, on how often a food product is consumed, and all kind of other factors might be used to determine the stringency of the plan that is needed. So you can see several other video clips in the playlist that in detail explain how this Icmsf sampling plan tool can work specifically with examples for Listeria monocytogenes and all the various parameters that have an influence on the stringency. So that is an overview of the video clips that we have done until now, and we now turn over to the question and answer section of this part. Thank you very much for the people that did post questions. There is still some possibility, but I now give the floor back to Leon to guide us through the questions.
Thank you very much, Marcel. And one of the questions relates to the last presentation. It's a question by Claudia Rangel, and she's asking, does the Codex Alimentarius have guidelines for microbiological criteria or for other organisms, not for Listeria monocytogenes only, related also to whether there's a risk assessment available? And indeed, Codex Alimentarius, since about 20 years, bases all its guidelines for microbiological control and good practices on risk assessments. So there's quite a long list of risk assessments available that have then informed, I should say, Codex Alimentarius guidelines. For instance, there are guidelines on viruses in food that have been informed by risk assessment, about STEC or Salmonella in beef, chicken, egg products that have a guideline based on risk assessment. Chronobacter, Salmonella in powdered infant formula, there's a risk assessment that has informed the Codex guidelines. And also there we have a number of video clips explaining that one. So there is a range of these sets of guidelines and risk assessments that you can download from the FAO website, the risk assessments, or the WHO website. And the Codex website will give you the guidelines. So hopefully that is a sufficient enough question. And we have a question also from Santana Leon. And maybe Marcel, would you want to take that one?
Yes, that is okay, Leon. And then the question is, what is the importance of sampling uncertainty and test method uncertainty, especially when these are required for conformity assessment? And this is specifically related when C = 1 and the M is very low, like 10 CFU per gram or 100 CFU per gram. So indeed, sampling uncertainty and test methods can have a very big relevance also on the performance of sampling plans. That is not really included in the statistics that we have explained today and that we explain in the video clips. However, it is also in certain cases relevant. However, in setting these criteria, you also include the sensitivity and the specificity of methods. And both these aspects can be relevant, the sensitivity and the specificity. If these limits are set, then of course, we should comply with these limits. We have discussed that also yesterday in one of the questions, where we had also the limit of 100 CFU per gram. And there also Wayne answered that for legislation, there is one strict limit. And that for that, I would like to also make a good comparison. If there is a certain limit set, which is based on risk assessment and which is based on risk management, and it is finally in legislation, then that limit should be complied to. And in setting that limit, you can include also measurement uncertainty, but if the limit is set, you should comply to that limit. And I would like to compare that if we set such a limit, for instance, with traffic lights. So we have an orange traffic light and a red traffic light. And if you pass a red traffic light and you're just 0.1 of a second after the light turned red, you can of course say, oh, it was only 0.1 second. The measurement uncertainty of that police officer will not have been correct enough. I would say no. We are talking here about safety. There was already an orange light, and you even did pass the red light. In the legislation, is the red light is really the limit. The orange light was already a warning. And that would be the good safety culture, that you are not discussing about these limits if it's 100 and if you're just a little bit above. If you are around that limit and start discussing about it, in my opinion, you have already the wrong food safety culture attitude. Because if you are very close to the limits, you should already be very concerned about things that are going wrong. Because, as Leon has shown in the last presentation also, that even if you have set these limits and you comply with the limit of 100 CFU per gram, for instance, still in the batch, there can be 45% of the samples that are above that limit. So even if you are below the limits, it does not say that everything is perfect in your batch. And there is always the matter of chance, and you only take a very few samples from that whole big batch. So we should not discuss about the accuracy of methods just around the limits. We should a little bit include it in setting the limits. However, if the limits are set, they are as they are set, and then we should not discuss anymore about this sensitivity and specificity. Of course, in certain cases, it can be very relevant if you have a certain food product and that you cannot, after, for instance, an acidification or so, very difficulties in resuscitating a microorganism and so on. Then it can become very relevant, even on the other side, that maybe your test methods are not good enough to detect the pathogen. That are specific examples where this should be maybe tested and validated that the methods are working well.
Thank you very much, Marcel. And there's another question on listeria in ready-to-eat foods from Yui Linton Pinto. Are refrigerated ready-to-eat salads considered as supporting the growth of LM? If so, what sampling plant should we choose? Well, you have many different types of RTE salads, I would think. If you would have leafy greens without any additions, that might be a medium that would support the growth of Listeria monocytogenes. But if you would have salads, leafy greens with that are somewhat acidified, that have maybe fruits in them or fruit salads, that would be kind of acidic, maybe the pH would limit or even stop the growth of Listeria monocytogenes. So those salads would possibly be not supporting growth of LM. And I think that is the essence of thinking about the way to choose the sampling plant. Do we have good information on the food product itself? Will it support growth in the way that it is intended to be prepared and handled by consumers? If it is reliably not supporting growth, then the sampling plan codex would advise would be a sampling plan looking at organisms levels lower than 100 CFU per gram. If there is a chance that the growth is supported, and then there would be a presence-absence test. There's a third possibility, and that is that you can prove to the satisfaction of the competent authority that within the shelf life of a product there is no exceedance over the 100 CFU per gram kind of limit. But in principle, you have to really understand the salad in the question of Pinto. And so next one, there's a question of Marianne Kubo, and she's a Brazilian living in France, and she noticed serious outbreaks, E. coli, pizza, chocolate, cheese recalls in several European countries. And I think she asked, what does that mean for the current and future food safety policy? it relates to a question we had yesterday when we also had a question about, well, people have established good, robust food safety management systems. Why do we still see outbreaks? In the sense of food safety policy, I think we shouldn't only look there. We need to look at the combination of what government policy is and what industry contributes to meeting that policy. So the policy sets the standards, the boundaries for what the government thinks is acceptable risk, is acceptable quality, wholesomeness that can be associated to food on market. So if there are problems, maybe those standards would be too lenient, but of course, the industry is trying to meet those standards, and setting up a solid food safety management system is key. Marcel introduced in one of the presentations this morning how a system is built up out of different layers, different components, and there could be things going wrong in how you build the food safety management system. I think it is very important that criteria and other test methods, physical chemical test methods are used to really monitor closely whether the system is performing as it is intended to be performing, using validated control measures. And still something can go wrong, but then we have to quickly catch that situation. We have to make sure that the feedback to things going wrong is working. Maybe we have process verification, trend analyses for that. Like John Donaghy mentioned yesterday, companies have more and more big data-based digital systems to really look at the problem occurring, notifying consumers, informing them about problems, but also finding the root causes of problems. So the whole system of the food safety management system, but also finding out how it works, that it works to the right way, is there. That is what we have currently. And I think many people are working hard to get that right. Still issues can occur, and we see that happening all over the world. Then the best thing to do is to quickly find the root cause, find the consumers that might be affected and alert them, make sure that there's no harm done. Problems cannot be 100% avoided possibly yet, and maybe in the future. Looking at time, I think we have opportunity for one or two more questions. There's a question on ISO standards from Nusli Sila. She's asking about the ISO standard for Salmonella, which is about composite sampling and the need for the user to validate the composition of samples. And the question is around, well, these protocols, validation protocols, are not within the reach of laboratories. So how does it work then? The other part of that question is FDA is allowing up to 15 analytical units of 25 to be composted. Yeah, the question is a little bit open. I think maybe I can give a first reflection and Marcel could add to it. But I think as a user, you would want to validate whatever you start using in terms of the standard for Salmonella. If you start using composition, you should validate that that works in your situation, that you have the capability and the capacity to do that, understand what the outcoming results mean. Of course, the ISO standards are kind of a good practice system, but it may be necessary to really check that they work for yourself. Some laboratories will be able to do it. Maybe not everybody has the capabilities. And if I think the FDA is allowing 15 analytical units, well, really, again, there you have to look at what is the purpose of using the protocol, what is the situation, and when compositing samples are used, what does it really mean to you? And if you find positives, what do you have to do if you have non-compliant situation? How do you dig deeper into the problem to find the root cause of it? Marcel, would you want to add to that?
I think that in this type of cases, concerted action between different organizations can be very useful, because for a certain food commodity, you have to validate this. But for instance, for powdered infant formula, also the International Dairy Federation or other or within a country, all the dairy factories together can show that these methods also do work. So you can have a concerted action. It does not have to be every laboratory that is testing, but that you have protocols that work and that you have shown that they are giving exactly the same results. So not every laboratory will be able to reach that, but with a ring study between different laboratories, you can do that, and then also maybe publish that in a new ISO document, or maybe in a scientific publication, so that it can be shared, because it is something where it is for the best of the benefit of everyone if we could make the methods easier but validated. We want to have the same level of safety, but of course in an efficient way. So concerted action is for the benefit of everyone.
Thank you,
Marcel. And then the last question, maybe, Leon?
Yeah, please go ahead.
Yeah, so the last question is that in Brazilian legislation, food service meals, so ready-to-eat foods, have to meet representative sampling and must be evaluated for every batch. And then in this case, Beatrice Lamanaka is then saying, so I would say that it's an every day of preparation. What do you think about this? What frequency would be recommended? So again, this depends, of course, again, for food service meal, for ready-to-eat foods, and what exactly the type of food is. That there is not one black and white answer, and also the way of preparation. And if, for instance, if it's a continuous production, or if you have a day-to-day production, indeed, if you have a day-to-day production, then every day would be a different batch. At least in the European legislation, it's not referred to that every batch always need to be sampled. You have to prove that in principle a batch would comply with this type of with the criteria. So it's maybe not needed to always every day take samples, and it depends. I would not say that the frequency of sampling there is one answer to that. It depends on the processing, on the product, and on the risks. And of course, with high risky foods, and if you do not have a dossier of a very long performance of compliance, then of course you need to sample more. But if for months you have produced in a clearly showing that you comply with the limits, you could reduce the frequency of sampling. Would you have to add anything to that, Leon?
No, I think that's perfectly right. The consumer is important. The food service situation is important. It's about the confidence on the one from the producer, and how that then relates to what testing you do. Maybe you also don't always need to do microbiological testing to have that confidence, but you have to do representative sampling to verify that you are in control day by day. Maybe in view of the time, we are already 2 minutes over. We should close the session. And in this session, we've been very much using, and yesterday as well, session 1, we've been using the video clips. And we may not have mentioned that to you specifically, but if you go to the Icmsf website and you look at these or other video clips, you can look at the button on YouTube at the bottom right, at the settings button, where you can change the subtitle. We're using them now in Spanish, but they're also available in Portuguese, and in English, in French, in Chinese. So you can change those around. And in particular, we want to thank Bernadette Franco and Francisco Garces, who have prepared the Portuguese and the Spanish subtitles for the whole series. So thank you for those. Please also thank you. Well, first of all, thank you for your questions today for this session. But please, if you have questions for tomorrow's sessions, do already launch them in YouTube. Tomorrow we will have 3 sessions, 3 panel sessions, so not really presentations, but open discussions on 3 different topics. We'll talk about current and future risk-based food safety management system. So we have already had some questions on that in these sessions. Until now, microcriteria, we will look in more deeply from around the world, and listeria there will be a panel session on listeria. So if you have questions on these already now, please send them in so the panel can look at them ahead of time. And in 10 minutes, 15 minutes from now, Session 4 will start. It will be moderated by Bernadette Franco and Michel Daniluk. And you will hear more about the application of useful testing to different types of commodities. That's it for us for the moment. Thank you very much. And I hope you enjoy the rest of the webinar. Thank you very much.
On behalf of Icmsf and the Latin American Subcommission of Icmsf, I'm pleased to welcome the participants of this session 4 of our webinar. I will chair this session together with my friend Michel Daniluk. Our first speaker will be Dr. Peter McLeod. He worked for Unilever for over 20 years, and in 2014, he joined Mondelez International in the UK as session manager for microbiology and food safety for Europe, Middle East, and Africa. He is member of the Icmsf since 2011. So Peter, welcome. You can start your presentation.
Thanks, Bernadette. Hopefully you can see the screen.
Yes.
Okay, good. So in this first session of this afternoon for me, we're going to be talking about ambient stable or heat treated foods. And those are a particular class of foods that are covered in one of the chapters in Book 8. So you can find this particular section in chapter 24 of Book 8, Icmsf Book 8, and this will cover the types of foods that I'm going to be taking you through now. So what do we mean by ambient stable or shelf stable heat treated foods? What are these foods? So the fact that they are stable means that they won't degrade or become unsafe during an extended storage at ambient temperature, and usually that means for more than 2 years. So these products are safe and stable, remain in that way for the closed shelf life of the product. Once you open these products, then you will see a degradation occurring quite quickly, as you do with other products. But the closed shelf life is more than 2 years. The definition of these varies between different countries and jurisdictions. And for example, in the US, these are referred to as low acid canned foods. And there's a specific set of regulations in the US that covers these types of foods. So you need to be thinking about open shelf life and closed shelf life. By closed shelf life, I'm referring to the period of time when the containers are not opened. After you open them, then you go into this open shelf life, which is a different consideration. So these types of foods include many types of different commodities, things like meat products, dairy products, fish products, vegetables, fruits, complex meals, so mixtures of different types of foods, soups and sauces. Many of them are you need to cook the product or to warm the product up. Some of them some of them are ready to eat. This does not include, or this generally speaking, does not include dried foods, and it does not include fermented foods. So by this definition of shelf stable heat treated, it refers to a particular types of foods that I'll go into more details about how these are processed. These have a very long history of safe use, and for many, many years. The concept of the heat treatment was originally developed by Nicolas Appert in France in response to a competition that was set in the country. And this process that he developed is commonly referred to as appetization. And Nicolas Appert at the time, it was using bottles and glass jars, and it was not the equivalent of a sterilization process. So it was boiling these bottles and glass jars for long periods of time, but they were not the same as what we would consider as commercially sterile today. So they were a little bit less heat processed compared to the F03 process that I'll describe in a minute. So this F03 process really came from the last bullet point on this slide, which was some work done by Esty and Mayer in the US in the early 1920s. And this is commonly referred to as the botulinum cook, which is also known as the 12D process. So these are just some examples of what we mean by ambient stable heat treated foods. You can see there are cans here on the left hand side. There are packs as well. You see these, the pack on the right hand side here, the curry made easy, is a good example of a development in packaging technology that has allowed a new packaging type to be used for these heat treated foods. And you can see some other forms of packaging in the middle at the bottom on this slide. So in book 8 and in book 6 as well, you will find information on different commodities that includes details of the main pathogens and toxins that you would need to consider for a particular type of food. So book 6 and book 8 are very good in describing the types of hazards that you would normally associate with these finished products, either coming from the raw materials or from the manufacturing process or from people handling the food itself. So for these heat processes or the heat processed foods, they will destroy vegetative organisms like Salmonella and Listeria. So in principle, you don't really need to worry about those. Those will be more than destroyed by the time and temperature used to heat these foods. So the main targets that are used for setting the time and temperature limits for these foods are Clostridium botulinum and to a lesser extent Bacillus cereus as well. So they're spore-forming organisms that are more heat resistant. And the data that Esty and Mayer generated back in the early 1920s was developed a little bit further into this 12D process. So the F0, this of 3, this means that at a temperature of 121 degrees centigrade, you need 3 minutes at that temperature to provide this 12D process. When you look at different other types of foods, so for example, refrigerated foods, then those foods, generally speaking, are less heavily processed because you're using refrigeration as part of the preservation of the food itself. And the target there is a lower log reduction. It's a 6 log reduction for non-proteolytic botulinum. So it's a lower thermal process that is used. Generally speaking, Bacillus cereus heat resistance is more variable than botulinum organisms. Another way of making these foods is to subject the food to an inline thermal process. So this is where you have a flow of the product through a line, a heating line, and it could be a plate heat exchanger or it could be a tube-in-tube heat exchanger. And then you pack the foods in a sterile environment. So this is where we refer to aseptic packaging, where the atmosphere or the environment in which the products are filled into the containers is made sterile using peroxide or other ways of making the environment sterile, and then the packs are sealed. And examples of these types of foods are things like UHT milk, aseptically packed soups, and some of the ready-to-drink coffees that you see on the market today. There is a third alternative, broad alternative to these, where the foods are subject to continuous inline thermal processing. They're hot filled and hermetically sealed, and then the containers are switched around. They're inverted in order to pasteurize the headspace. So it's like a clean fill operation, if you like, where the headspace is pasteurized, taking the heat from the product that you're using to fill the container. So what technologies are used for these products? The main technology used is retorting or a steam sterilization process. And for retorting, generally speaking, you're using a steam infusion or steam injection. You're injecting steam into a container, pressurizing that, and using the heat and time and temperature to introduce your sterilization process. You can use in aseptic processes, tubular heat exchangers or plate heat exchangers, where you're indirectly heating the product through a plate or through a tube. And again, the basis of the sterilization process is reaching a minimum time and temperature. If you look at more recent technologies that have been used or applied to foods using for ambient stable foods, there are other examples of these technologies. One is ohmic heating, where you're using a current, electric current between a cathode and an anode in a heating in a treatment vessel, and you're heating the food using that electric current. You can also use microwave assisted thermal sterilization and also high pressure assisted thermal sterilization as well. The graph on the right hand side here shows you the rise in temperature that you will see if you pressurize a container with food. So when you apply the pressure, you get a form of heating that's called adiabatic heating. So that the actual pressurization of the food will introduce more heat into the food. It takes the heat up more quickly, and when you release the pressure, the temperature comes down very quickly as well. So it's a way of better control with the thermal process. But still, the basis of these processes here, these three alternatives, ohmic heating, microwave, and high pressure assisted thermal sterilization, the basis is time and temperature of heating. The fourth example, irradiation, is a completely different process where you are relying on a radiation dose to deliver your sterilization. So that does not rely on time and temperature. It relies on a radiation dose rather than time and temperature. So the key message from this are that the key parameters that you're interested in are time and temperature of the product during that heating cycle. These are just some pictures of typical products, and the little diagram on the left-hand side here at the bottom is a computer-generated map of the thermal process, the thermal map within a pack of food. So the pack's on the right-hand side here. If you flip the pack on its side and then you predict what the temperature will be inside the pack, you can predict the temperature achieved at the coldest point within the pack. So a number of food companies have this technology where they can predict the temperature. So it's a good way of telling you how quickly you can expect the food to heat inside the pack, but you would always validate this by taking some actual measurements in the validation process. So are heat-treated foods, ambient stable foods, still important? Yes, they're still very important. And we've seen this emphasized through some recent changes, through fuel shortages, the COVID-19 lockdowns. What you've seen is people going for types of foods that are stable, going to be stable in their kitchens, on their shelves, and they don't need to go out as often to stock up on these foods, so they can stockpile for longer periods of time. So these foods are not going away, even though there's been a massive change in the introduction of fresher types of foods and refrigerated foods. These foods are still very popular. These are just some slides showing some consequences of things that have happened recently, and even the situation with the war in Ukraine. Recently in the UK, we've seen these signs going up in the supermarkets saying you can only take 2 containers of sunflower oil because of the limited supply of sunflower oil now in the UK as a consequence of the conflict in Ukraine. So I'm going to take you through some examples of where things have gone wrong for ambient stable heat treated foods. This first one was a hot dog chili sauce that was made by Castleberry Foods in the US, and it was an outbreak of botulism. This is a very good example of a HACCP study going wrong. So where the controls, the critical controls in terms of time and temperature, were not properly maintained, There was a huge recall, 39 million cans, was expanded to 110 million cans, because when the FDA went in to inspect the manufacturing facility, they found that the bad practices in place there had been going on for nearly 2 years. So they couldn't guarantee the safety of these products going back that period of time. So that the important point here was about a failure in delivering the critical control point, the time and temperature that was needed to make these products sterile. Another example of a failure in manufacturing was some years ago now with John West canned salmon. And the problem occurred because there was a problem with, well, there were two problems. There was a problem with the cans that were used to contain the salmon. They were, in the way that they were shipped to the manufacturing site, they introduced some pinholes in the seams of the cans. So these cans had pinholes before they were filled. So there was no problem with the processing at all of the salmon. And the salmon was cooked properly in the can. But then the cans were taken outside. The operators, the people who had gutted the fish, had spores of non-proteolytic botulinum on their overalls. They would take their overalls off, put them onto the warm cans to dry the aprons. And when the cans were cooling, they were taking in moisture and air from the outside. And of course, on the outside of these cans now, you have these aprons with spores. So this is how the two bits of bad practice, putting the aprons on the cans, but also not realizing that they'd introduced a problem with the packaging by damaging the cans before processing. This is how this problem came about. A third example here is an outbreak linked to bottled peanuts. This is a very good example, a parallel with the process that Nicolas Appert used and developed in the 1800s. In this case, these jars were cooked by boiling, so boiling the jars for a long period of time. It delivered some log reduction, but not enough. And in fact, this product had been made for more than 6 years without any apparent problem. But the manufacturers didn't realize that they should have been delivering a 12D process rather than a 3 or a 5 log process that they were effectively using. So it was under processing, a failure in their HACCP plan. One other example that I'd like to talk about is about a change in pack size. And in this case, some canned soups had been made very safely, no spoilage problems for many years. Production was switched to a new manufacturing site that didn't understand the concepts and the important factors involved in processing these cans. They made a change to the pack size. There was a change in the proportion of the size of the pieces compared to the larger cans. And in fact, what they'd done without understanding it was they changed the thermodynamics of the product heating. And they'd gone from a situation where in the original cans, there was convection heating to a situation where there was conduction heating. And conduction heating is not as effective as convection heating. So the product inside the cans was heating up slower than it would have been if they'd been in the original can size. And they noticed the problem by these cans blowing, swelling, and by gas formation inside by spore formers. If they'd done a proper validation, checking the temperature inside the can before they'd manufactured the product and released it to the market, then they would have noticed this problem. So this demonstrates the importance of validation of the CCP. So there are several things that need to be met to make a safe product: clean equipment, good quality raw materials, clean containers. All of these things here are important for ambient stable heat treated foods. And for novel processes, you must validate for target organisms. Generally speaking, if you're making a canned product, let's say a canned meat or a canned soup, generally speaking, we refer to that as a safe harbor. You don't need to validate that the time and temperature will deliver your 12 log reduction, because the process is so well established that you don't need to validate the process itself. What you need to do is check that your times and temperatures are met in your container inside the can. So this slide talks a little bit about safety by design, and you can find very good information in Icmsf books 5 and 6. These books talk about the combinations of preservatives, the processing options that people are using for different types of products. They'll talk about packaging and storage conditions, and about monitoring for control as well. Important to mention, I think, that monitoring emerging hazards is also important. And generally speaking, if you find that in your product design, you don't have good information to support that your process is a valid process to use, so for example, like a safe harbor, then it may be necessary to do challenge tests to verify that your product design is safe. So this is just a picture of book 6. It tells you about the important organisms to consider in your process for this group of foods. There are some critical ingredients for ambient stable heat treated products. So the quality of the raw materials is important, particularly things like sugars, starches, and spices. So these are the types of commodities that will harbor loads of mesophilic spore formers. So the mesophilic spore formers, like Clostridium botulinum, like the bacilli, like some of the spoilage bacteria as well, the spore formers, they are very good examples of mesophilic spore formers that could be a threat to your process if you don't heat for a long enough time. So it may be appropriate to set microcriteria for some of those materials. And I think there's a slide right at the end of the presentation which has some suggested limits for some types of these commodities, which were identified by the National Canning Association in the US some time ago. The specifications are also dependent on your final storage conditions. So, for example, if you're in a very in a climate where the temperature is very high or can get very high, it may be that thermophilic organisms then become a problem for you because they're not able to grow at the lower temperatures. But when the products are stored at, let's say, 38, 39, 40 degrees centigrade, then those are the temperatures at which these more thermophilic organisms are able to grow, and they will become a problem. And in some countries, there are specifications which are set for these organisms in different product types. It's important to use appropriate methods including heat treatment and recovery of enumeration of spore formers when you're doing these tests for these particular types of organisms. So this is a critical slide for this group of products. When you look at the information in Book 8, it will include, for every chapter, it will include a table like this, which will tell you whether the relative importance for testing of different components like critical ingredients. So for these groups of products, for critical ingredients, the importance is medium. So you should be testing for bacterial spores in starches, sugars, and cereals and spices to get some information on the quality of those materials. And this does cover, there is seasonal variation that you will see with these commodities. So it's good to generate the data over a period of time to give you the confidence that the quality of the materials that you're sourcing from your suppliers is good and acceptable. You'll notice that in process sampling, the importance is low. Maybe the only areas where you would want to do testing for in-process samples is cooling water, where the cooling water is used to cool the containers. And the frequency of that testing would depend on the water source itself. In the processing environment itself, there's really very little point in doing testing in and around the processing environment. You can test for hygiene monitoring for critical pre-thermal process production steps that may allow increase or allow growth of spore formers to occur, but you wouldn't do the same type of environmental testing that you would do for, let's say, a more sensitive product like a dairy powder that John will talk about later on. And then for validation of cleaning, this is more important for these products. So in many processes for these types of products, there are steps in the process where you will use equipment after the sterilization process. And let's say when you're pulling a vacuum and then after you've introduced water and the products are going through some different equipment. Very often you need to check the cleaning, that equipment is properly cleaned and properly and in a good hygienic state. And that's where you would want to do some testing of this type of equipment. In terms of shelf life, it's really of low importance. For end product, you would not do routine testing for the finished product. You would only do testing when you have a problem, when you're investigating spoilage incidents, when you've got some thermophilic spoilage or post-process contamination via water cooling or something else. Also, you may want to do testing where you're verifying a process, for example, in aseptic filling operation. So commonly in an aseptic process, when you set up the aseptic process itself, you would do a lot of testing on cans or containers when you first set up the equipment. That gives you the confidence then that equipment is working well. And there's a section in Icmsf book 8 and book 7 on testing for aseptic type processes. So testing for pathogens, consistent with Codex, you only should do testing when there's good evidence that the product type has been implicated in foodborne disease, or you may not have an adequate shelf life, and only when you believe there's value from doing the testing, from, let's say, for example, when it will reduce the health risk associated with a food. One important point to mention with these types of foods and this blowing effect that you see with cans sometimes, when you're looking at a defect rate, please do not rely on a visual inspection of cans that are blowing to tell you what the defect rate is. The best way to understand the defect rate is to open the can and do a pH test on the product or do microtesting, because there are some cans that will blow and some other cans that will not blow. So by just looking at the blowing cans, you will underestimate the defect rate that you have. So while microtesting is an integral part of micro food safety programs, it must be used appropriately and pragmatically. As we've said before in the previous presentations, no food safety program can rely solely on microbiological testing. And for shelf-stable products, the most useful measurements are the physical measurements that can be related to survival and potential for growth. And here, the emphasis is on assurance of the control of the process itself, not on microbiological testing of the finished products. Despite that, as always, you need to follow the legislation in your country, and that must be applied and complied with. The last slide here gives you some example. I'm not going to go into detail about this slide, and just to say that for tomorrow, in terms of the question that we had earlier on causes of incidents and underlying causes that Leon mentioned, maybe I'll get a chance to take you through some information that tells you more about the causes of failures in processing. Thank you, Bernadette.
Thank you, Peter, for this nice and comprehensive overview on heat-stable food products. Our next speaker is Dr. Kiran Bilagankar. He is the principal scientist and in charge of the regional center of the Indian Veterinary Research Institute in Pune, India. He is member of the Icmsf since 2011, and he was consultant also from 2008 to 2010. I welcome Dr. Kiran for his presentation now.
Thank you, Bernadette, and greetings of the day. Just a minute, I'll share. Okay, is it all fine? Is
yep,
it okay?
You're good. Yep,
Yeah.
You're good.
Right. So the next part of the book 8, which I am talking about, is the chapters on poultry and other meat products. All the applications of sampling and testing principles, which since yesterday we have been listening to. So my presentation outline is I would be just talking briefly about the introduction of meat and meat-borne pathogens, their importance. Then I would be dealing with two commodities from each of these two chapters, that is poultry chapter 2 commodities, and then from meat and meat products, two different products I'll be dealing with. As we know, meat is a very important international commodity. And when you see most produced food commodities by value in the world, we have three different meats like pig, cattle, and chicken meat, which stand out, and they are among top 6. In recent times, in last 5 decades or 5.5 decades, almost 4 times increase has happened in the meat and meat trade. When we see by quantity, the maximum quantity of meat production in the last several years, and there is an increasing trend is of chicken, followed by pork, and then beef is the third number. Chicken meat is one of the fastest growing meat sector, and in last 20 years, almost 44% growth has been seen in the chicken meat since 2000 to 2020. And when we see the trade of different types of meat by quantity, again, the poultry meat stands out, chicken meat stands out. It's a maximum quantity trade. And the FAO Agriculture Outlook, they have predicted that it is going to be, growth is going to be faster in chicken meat. And in terms of value, the maximum value by different type of meat is for beef, followed by then chicken, and then pork. The meat trade, maximum meat trade is happening either from USA and Brazil to different countries. For poultry, you can see here graph, these are very recent 2019 figures, and for world beef trade, it's 2020 figures. Again, a similar trend, you can see it's from USA, Brazil, maximum trade is happening, and export is happening to all over the world from these two countries. Beef, of course, there is some, Australia also is contributing to some beef export. As we know that meat is an excellent support system for the microbial growth, and then it becomes a very important source of all the foodborne pathogens. We know Listeria monocytogenes and Salmonella, they are one of the most important pathogens, and frequent outbreaks have been seen world over because of these two pathogens. Campylobacter species is a prominent for our poultry product across Europe or other countries. Yersinia enterocolitica, specifically for pork, it's a very important organism. Recent times, enterohemorrhagic E. coli or O15787 and other serotypes of E. coli, enterohemorrhagic E. coli, they have become a very important emerging pathogens, particularly in relation to beef or other sheep and goat meat. Clostridium perfringens, basically it's a spore former, so time, temperature, abuse, post-cooking, and survival of spores in large catering events leads to this kind of outbreaks, or uncured meat product also. They have some reported outbreaks for Clostridium perfringens. When we see foodborne illnesses by commodity, this is a little bit old paper from United States of America. You can see here again, out of the top 6 different food commodities contributing to the foodborne illness, top 4 are meat. That is poultry, pork, beef, and different type of daily meat products. So major contributors for foodborne illness again by product type is meat and meat products. As I have said, the book 8, 2 chapters I am going to deal, that is application of principles to the meat product, which is in the chapter 8, and then application for the poultry product, which is chapter 9. I would start with the poultry product chapter. This chapter has been divided into 4 different poultry products, that is raw poultry product, cooked poultry product, fully retort or shelf-stable poultry product, already dealt by Peter, then dried poultry product. Just because of want of time, I would be just touching only 2 of these poultry products. Each of these product categories, they have all further subdivided into subheadings. What are significant organisms for each of these categories? What is the relative importance or usefulness of data related to microbiological testing for critical ingredients? Peter has already shown you table. That table is there in every chapter, whether there is an importance of testing for critical ingredients, whether there is an importance, relative importance for testing in the process, product testing or any other tests which are needed, whether processing environment has to be checked for any contamination, shelf life stability has, whether it's important, and then end product, what tests have to be conducted for end product if they are important. The poultry product chapter starts with a little bit information about the primary production. And as we know, world over, there are mainly 2 production systems that exist. Usually there are small farms which are in the extensive type of production system. And these small farms scattered all over places, the control programs are very difficult, particularly Salmonella, Campylobacter, etc. In case of large, intensive indoor productions, there are better measures which we can take for control of Salmonella and Campylobacter. But this chapter doesn't detail out the control measures and doesn't describe in detail all the control measures. You can refer back to the Codex guidelines, which gives a control for Campylobacter as well as Salmonella in chicken meat. There are control measures which have been described, which are GHP-based control measure as well as hazard-based control measures. So you can go through all these control measures in Codex guidelines. The first product category is a raw product. The important pathogens for this category are Salmonella and Campylobacter. And as the table describes here, for the critical ingredients, it's usually only raw poultry. So there are no other ingredients which are used. Sometimes some ingredient like some salt or vinegar may be used, but it is not recommended to test. The only important thing here is time temperature, quick chilling for the poultry, raw poultry pieces, cut pieces, or the carcasses, whatever it may be. Quick chilling is very important, time temperature. In process testing is of medium importance. You can go for testing the whole carcass rings or particularly neck tissue samples, which will give you a baseline information about the organisms which are harbored at different stages of processing. And this baseline will give you the correct information, and then you can go ahead with your hygiene practices and control measures during the processing. The processing environment, again, it's of a medium importance. Particularly before start of the operation, you can verify the efficacy of cleaning and disinfecting procedures which you are following. And usually Icmsf recommends that less than 500 CFU per centimeter squares must be, these levels are relatively good and safe. Shelf life stability, it is not recommended for either refrigerated or for frozen product. Only when there are certain new packaging systems or some new retail product which is coming, you can validate the code dates and check it for the shelf life. Regarding end product testing, it is of medium importance generally for indicator organisms, which will give you the idea about the process control and trend analysis. These can be tested for aerobic colony counts. They should generally be less than 10 to the power 5 or E. coli less than 100 CFU per gram. But this is only at the factory level and not for the retail product or distribution chain. Acceptance lot sampling, Icmsf doesn't recommend for Salmonella or Campylobacter, but for the outbreak investigation or for the new supplier certification, we can go for these testing for Salmonella and Campylobacter. In some of the countries, regulations, they have established performance objective at certain stage of the process for the Salmonella testing or Campylobacter testing, and these need to be applied in these countries. The second product is a dried poultry product. For dried product, the most important pathogen is Salmonella. And since again, not many non-meat ingredients are there, so critical ingredients is only poultry parts or parts of pieces of poultry. So it's of relatively low importance for critical ingredients. In process testing, Icmsf recommends that it is of high importance, particularly for process. It should be validated for control of Salmonella. All the cooking parameters or formulation parameters like pH or preservatives, they should be able to reduce, or they should be able to control the Salmonella properly. So it's of relatively high importance. But for microbiological testing, it is not recommended. It's of low importance. Processing environment, again, before the start of the operation, we can verify the cleaning and disinfections. It's of medium importance. Shelf stability testing for microbes, generally it is not recommended. They are inherently shelf stable products, and if properly control water activities and if we are taking care of the molds, there is no problem in these products. The end product testing, again, only when there is a HACCP or good hygienic practices are in question, it is recommended to test it for Salmonella. And Salmonella testing, Icmsf recommends case 11, that is 10 samples to be tested. This case 11 deals with the organisms where there is no growth or no reduction in organisms. So 10 samples, none of them should have Salmonella, and 25 grams is the sample unit which has to be taken. When the plan performance is checked through the sampling tool Marcel has already told about, you can see here 95% of the times there is a probability of rejection in this sampling plan, that is n is equal to 10, c is equal to 0, m is equal to 0. When there is a one cell present in 180 gram at the standard deviation of 0.8. Depending on the distribution of microorganisms, there will be different performance of these sampling plans. The second chapter is chapter 8, meat and meat product. Again, this has been divided into 8 different categories, starting from raw meat to raw comminuted meat and cured meat to shelf stable meat. So 8 different categories have been described in this. Again, I'll be dealing only with these 2, raw comminuted and raw cooked meat product. Again, meat product chapter also again starts with the same primary production. Again, it's a similar situation in this case also. Small family-owned farms versus large commercial farms where pathogen control is better. Again, detailed control measures, you can go and refer to the Code of Hygienic Practices for Meat by Codex, or a recent guideline for control of non-typhoidal Salmonella species in beef and pork meat. This also gives a good idea about control of Salmonella. The first category which I would be describing is raw comminuted meats. The important pathogen, there is a long list of pathogens which are important for this. Salmonella, as we know, as well as Listeria monocytogenes, for all type of meat, these two pathogens are very important. Enterohemorrhagic E. coli, beef, lamb and goat meat, it's important. In some cases, Campylobacter coli for pork, and some other organisms like Yersinia for pork, they are also important. There are different examples of these type of products like burger patty, puddings, koftas, and kiftas. So these products usually have a different type of additional ingredients like wheat flour, rice flour, herbs, binders, all these types of or spices in them. So for critical ingredients, it depends the testing from low to high importance. In case of beef trimmings, where there is a chance or there is already confidence is low that there are chances of having E. coli 015787, then pre-testing of the beef trimming for this particular pathogen or enterohemorrhagic pathogen may be of importance. And then the sampling plan recommended here is 30 samples to be tested. I will be showing it again in the end product testing also similar. In process testing, it is normally not recommended in process collection of samples at different stages, but for the factories, they can go at various stages of processing to establish baseline and the microbial population growth, how it affects, how it changes during the processing. It can be established. Processing environment, it's again similar thing for all meats. You can verify the efficacy of cleaning and disinfection before the start of operation. Shelf stability, it's of low importance. Usually these are refrigerated product. It is not recommended. Sometimes for new packaging system, again, it's for similar that like raw product, you can validate the code dates for either new packaging system or for new products. End product testing for indicators for ongoing process control or trend analysis, it's of medium importance. You can test Icmsf recommends for testing of E. coli case number 4. 5 samples should with 3 samples having counts between 10 to 100 and none above 100. So this is a 3-class sampling plan which is recommended. For Salmonella, usually routine testing for these raw comminuted meat sample is not recommended by Icmsf, but for E. coli 0157, wherever there are regions which have already shown the prevalence or the outbreaks, it's of importance. And the case number 14 with 30 samples of 25 gram each is recommended for testing. And when we see plant performance here for the 3-class sampling plan for E. coli, you can see here 95% of probability of rejection when there are 51 CFU per gram of samples for E. coli. But as you can see here for E. coli, the N is equal to 30, C0 and M0, 25 grams. Even one cell is present in 850 grams at the standard deviation or distribution of 0.8. The 95% of times probability of rejection is there. The next category is the cured and uncured cooked products. Again, these are perishable. Usually they are frozen or chilled products. Several type of cooked products are there. A very long list of pathogens is they have been found to have incriminated into the outbreaks because of consumption of these cooked meat products. Salmonella, all meat product, Listeria monocytogenes, again, all meat product. Clostridium perfringens, particularly important in uncured, as well as I have said that cooked products which are not kept properly post-cooking, temperatures are not refrigerated or not lowered down, and the survived spores can then multiply, and this is one of the big problems whenever there are mass scattering events happening. Staphylococcus aureus, usually it's a post-cook contamination which are not packed foods. This may be a problem, concern. And there are other organisms like Campylobacter forte or Yersinia forte. The critical ingredient testing, again, it's low, it's of relatively low importance. Even non-meat ingredient testing is of not much significance because of the heating process which is being used. In process, time temperature combination, particularly cooking parameter, is very important. And this is of the high importance recommended by the Icmsf. You have to monitor it very stringently, the time and temperature, as Peter has already shown the core temperature, particularly heating temperatures, they have to be monitored correctly. For microorganism testing, it's of medium importance, particularly for this for the products which support the growth of Listeria monocytogenes. So post-cook samples can be checked for the Listeria species, and they should be absent in the post-cook products. Processing environment, again, for Listeria monocytogenes, wherever there are chances of growth in those products, the contact surfaces, they can be checked, and they can be continuously monitored for the presence of Listeria, or rather the all surfaces should not have any presence of Listeria. For processing environment, again, the microbiological testing for aerobic colony counts before start of operation, verification for cleaning and disinfection can be of importance. Shelf stability may be useful for refrigerated products if there is some extended shelf stability or extended dates are recommended. For frozen product, usually the testing is not recommended. In case of end product, for indicator, the recommendations are for aerobic colony counts. Here, the level should not exceed 10 to the power 5. For E. coli, level should not exceed 10 to the power 2. Even for Staphylococcus aureus and Clostridium perfringens, Icmsf recommends. For Clostridium perfringens, it's particularly for uncured meats. Levels, they should not, it's a 3-class sampling plan, 5, 1, 10 to the power 2, and 10 to the power 3. So one sample can have counts between 10 to the power 2 and 3, and none of the samples should have counts of more than 10 to the power 3. For pathogen testing, usually it's not recommended. If good hygienic practices and HACCP system is in place, all control measures are in place. But there are, whenever there are question marks on these systems, it is recommended. For Salmonella, it's the same case number 11, 10 samples with 25 grams. For Listeria, the codex recommendations can be used, those that support the growth, 5 samples, none of the samples should have a presence of organisms. For cooked meat, which do not support the growth, 5 samples, up to 100 organisms, these recommendations are given by Icmsf. The plan performance I have already dealt with for E. coli. For the Listeria monocytogenes, here you can see one cell in 55 grams with standard deviation 8 will be able to detect this sampling plan at the 95% of the probability. So finally, to conclude, microbiological testing, it's a very integral part of the food safety management system, but you have to use it very pragmatically, and appropriate testing at appropriate steps is important. And you should not rely only on microbiological testing. All other safety programs, monitoring temperature, time, all these things are very critically important. As emphasized, these are just guidelines, ICMSF recommendations, and everybody has to follow all the standards of national or international trade regulations which have been given by national agencies or international agencies. And as Marcel has already shown you the ICMSF sampling plan performance calculator, which you can download and check the alternate plans for the similar performance. So thank you very much.
Thank you, Dr. Kiran, for your very complete presentation. And I would like to introduce our next speaker, which is Michelle Daniluk. Michelle Daniluk is an associate professor of food safety and microbiology in the Department of Food Science and Human Nutrition at the University of Florida, USA. Her interests include microbial food safety and quality with focus on fruits, vegetables, and nuts. She's member of the Icmsf since 2016, and she's the treasurer since 2018. Welcome, Michelle. I pass the word to you.
Perfect. Thank you, Bernadette. Glad to be here, and hello to everybody listening in today. So I'm going to talk a little bit now about the application of these sampling plans to different types of fresh produce and fresh produce commodities. I want to start by acknowledging my colleagues on Icmsf, Dr. Lucia Analich and Dr. Robert Buchanan, who have both contributed slides for this presentation at different times. So with that, I will get started. So I want to start with a discussion similar to both Peter and Kiran about talking about what is produce. And so, as Bernadette says, I work with produce, but it's many different types of foods that are derived from plants that does not include things like grains, nuts, and some legumes. So we're talking primarily about vegetables, we're talking about fruits, we're talking about certain types of fungi or mushrooms, and then we're talking about sprouted seeds in this category as well. Certainly a very important part of the human diet as a source of nutrients, fiber, and vitamins. Certainly something we see governments encouraging people to eat more of. And as we see more people being encouraged to eat more of it, people being encouraged to eat fresh and fruits and vegetables in their raw state, we've sort of seen an increase in the number of foodborne illnesses associated with them. And if we look historically, many of these different fruits and vegetables would have been preserved in some other way by freezing or by canning to eat them in the off season, whereas now, because of the international trade, we're able to enjoy fresh fruits and vegetables year round. This is data coming out of the United States, and it is outbreaks associated with fresh produce between 2010 and 2017. So still a little bit older data, but it talks about the percentages of outbreaks sort of in each of these different categories. So we can see that at least in the United States, those sprouted seeds account for a huge number of illnesses. I'm going to go ahead and modify this data that came out of a publication from back in 2019 onto this next graph where I will show, where I will remove sprouts from the equation because they're very much different than a lot of other types of fresh fruits and vegetables. And I've grouped all the different types of leafy greens together. So I've put the lettuce and the romaine and the different varieties of lettuce all into that one category. And we can see there that again, this leafy green category after sprouts really is another major contributor to fresh fruit and vegetable safety or to outbreaks related to fresh fruits and vegetables. But then there's a bunch of other commodities that we'll talk through that are also major contributors. So melon, specifically the what we would call in North America cantaloupe melon or musk melon in other places, but those netted melons are major contributors as well. We see papaya very high on the list afterwards as well. That's driven by a couple of salmonella outbreaks of papaya being imported into the US from Mexico. Cucumber is one that, especially in the last 5 years, has popped up many times as being associated with outbreaks. Tomatoes have been on this list for a long time. I will say tomatoes, maybe 2 decades ago or a decade ago, were similar to greens in terms of the percentage of outbreaks that they caused. And so we do see the number with tomatoes coming down because of some of the practices that tomato growers have adopted. Mangoes, again, pop up pretty regularly on our list, often having to do with some of the post-harvest practices we do with mangoes, especially mangoes that are being imported into the US to control some fruit fly problems, of course, and then peppers are up there as well. And then that 10% of other that we see a lot of different types of commodities falling into that I'll talk through a little bit on a couple of next slides. If we look just beyond sort of commodities causing illnesses, and this is data out of 2018 from the Center for Disease Control in the US, what we see is that if we look at plant-based outbreaks, those plant-based outbreaks are less than we see coming from land animals or aquatic animals. But if we look at the number of illnesses that those outbreaks have caused, really, and that's looking at this data right here, almost 10,000 illnesses in that 6-year period, almost equivalent to what we would see, with our land animal disease outbreaks, those meat products that Kieran talked about just before me. So again, tremendous burden of foodborne illnesses coming out of these fresh fruits and vegetables within the United States. Broken down by category, we can look at them here. Again, sprouts, you see a major contributor. We see seeded vegetables here also being very high. Seeded vegetables in this case is what we would call the solanaceous crop. So that includes tomatoes, eggplants, peppers, and most vegetables that are vine grown. So cucumbers would also be included here. And we also see fruits popping up very high down here at the bottom. Those fruits include all the different fruits. So our plum fruits like apples and pears. The melons would be categorized in here. All our small fruits, so that includes all the different berry categories, plus the tropical fruits, the subtropical fruits like citrus, and our stone fruits would also be included in that category. The other one that's very high is the one right above it, and that would be these vegetable row crops, and that's what we consider where we would put all our leafy greens and leafy stems in that category as well. So really those categories that we see causing the most outbreaks, we also see causing the highest number of illnesses over time. When they break that down a little bit further into top pathogen food commodity pairs resulting in outbreaks, again, depending on the different category, we often see commodity pairs for fresh fruits and vegetables with different pathogens pop up. So if we look at, in this case, total number of illnesses, Salmonella in those seeded vegetables comes up number 2 in terms of our pathogen food commodity pair. Again, those seeded vegetables being things like tomatoes, peppers, and cucumbers. If we look then at the category by hospitalization, again, we can also see we can see 3 of the top 5 pathogen food commodity pairs are linked to fruits and vegetables. Again, Salmonella seeded vegetables coming in at number 1 in terms of hospitalizations. Salmonella in fruits coming in at number 3, and then Salmonella and Listeria monocytogenes in fruits coming in at number 5. That Listeria fruits outbreak is really driven by one outbreak in the US back in 2011, so just over a decade ago, associated with whole cantaloupe melons and Listeria monocytogenes. So driving that number where it is. And then finally, if we look at deaths, also 4 of our top 5 pathogen food category pairs within the US between 2009 and 2015 were related to some sort of fresh produce item. Again, Listeria and fruit coming in at number 1, those 41 deaths primarily being linked back again to that cantaloupe Listeria outbreak from 2011. But we also see Salmonella in our seeded vegetables, Salmonella in our fruits, and Listeria in our vegetable row crops or leafy greens also popping up very high on this list. So there's a tremendous burden of foodborne illness caused by pathogens, particularly bacterial pathogens in this case within our fresh fruit and vegetable crops. So I just want to highlight a couple of notable outbreaks, some older, some newer as we go through. This is an outbreak that happened in Europe, and it was hepatitis A, and it was within 12 European countries. And it was caused because of frozen mixed berry products, the kind of berries you would purchase in a frozen form and then throw into a smoothie, add to a sauce, have a lot of different uses for, again, 12 European countries and at least 1,444 cases. They had 2 suspect origins for where this outbreak may have come from, and it was really related back to high-risk practices during freezing, again, particularly related to the workers handling the berry products before they went into that IQF freezing process. Highlight this one that happened between March and June 2018 here in the United States. This one is notable because of its complex traceback operation. So I've highlighted that traceback operation on the right-hand side of this slide. It was associated with romaine lettuce grown in Arizona, in the Yuma, Arizona area. E. coli 015787 was a positive agent. Again, something we see frequently associated with leafy green production coming out of the Western US. Illnesses within 36 states in the US and in Canada, 210 total people sick, 96 ended up in the hospital, 27 were associated with some sort of hemolytic uremic syndrome, and actually 5 deaths linked back to that. What's interesting in this case is that they never traced the outbreak back to an individual farm, but rather back to a large growing region that was all pulling water out of the same series of canals, which is how they got their overhead or their irrigation water. And they were able to find the outbreak strain in the canal close to a feedlot. And then again, just very complicated trace back where they were able to go back to a number of different manufacturers on a number of different farms and in a number of different fields on that farm. Again, the hypothesis is the strain came out of the irrigation water that was used on all those different operations. This is different. There were 2 U.S. outbreaks of E. coli 015787 related to romaine lettuce in 2018. The second one happened in the fall of that year, and that was romaine lettuce coming out of California. In that case, they hypothesized, and in that case, they were able to find the outbreak strain in another surface water source. In that case, that surface water source was being used to both wash equipment and wash the leafy greens. It was being treated, but there were deficiencies noted in how the water was being treated, specifically in how the chlorine was being dosed into the water prior to treatment. Different outbreak. Talk about a more recent outbreak now. This is an onion outbreak that happened in the US and Canada between June and October of 2020. It was related to red onions grown in California specifically, but because the operation was unable to show a clean break in their production, they had to recall all onions they ran through their packing operations. So while red onions in particular were linked to the outbreak, the yellow, white, and sweet yellow onions shipped between May and August were all part of the recall in this case. This is the largest salmonella outbreak in over a decade to occur in the United States. 48 states had illnesses linked to this outbreak, 1,127 cases within the US, an additional 515 cases in Canada, and 167 different people hospitalized. First outbreak associated with whole onions had previously seen outbreaks of salmonella associated with onions that were cut over time, cut and then stored and improperly refrigerated over time. But this is the first case of it being whole onions. The hypothesis of where this outbreak came from, again, is contaminated water. And I've got the link there on the bottom to the comprehensive report that FDA put out. But again, this is their traceback operation to get back to these onion fields. So you can see that, again, it was a quite complicated traceback with a bunch of different points of service going through a bunch of different distributors, eventually linking back to one grower. And then that grower had fields in different locations within California. Again, this comprehensive report out of FDA really can show some of the work they're doing to trace back and look for sources of these outbreaks. In this case, this is a field out of Hotville, California. So that's this first field up here at the top. Complicated picture looking at it, but the red, what's important to see here is the red here is the onion field. The two white here where they had sheep grazing. All the different blue lines are irrigation water canals. The red lines are where we would have irrigation water drainage. And then every place there is a dot is somewhere they found Salmonella in the environment. The red dots are Salmonella Newport. Salmonella Newport was the outbreak serotype of Newport. They did not find any matching genetic fingerprints to that. And then the yellow dots are other types of Salmonella in the water. They did find, and I'll point out this blue square in the middle, this blue square going on right here. They found another type of Salmonella that had previously been associated with a sprout outbreak. But a tremendous amount of Salmonella they were able to pull out of the environment. The grazing sheep adjacent to that field was something they highlighted very highly in the report. Something we're continuing to see from FDA is their highlighting of adjacent animal agriculture to produce production. This is another field associated with that outbreak again. Same Salmonella species in the onion field in this case. In this case, they identify very close concentrated animal feeding operations, in that case cattle, that was quite in quite close proximity to the onion field, and it was identified in their report as something that was likely a contributing risk factor to the outbreak. This idea of adjacent land use leading to fresh produce outbreaks is something we're seeing more and more here within the United States, being highlighted by FDA as a risk factor. This again is another outbreak from 2020. This is related to whole peaches that were consumed within the US. 17 states involved 101 cases and 28 hospitalizations, Salmonella enteritidis. In this case, they were able to go back to the peach orchards, which are highlighted here and here. And one of the things they highly call out is that the adjacent use of land, in which case is a poultry boiler farm here and a dairy farm here, are likely high contributors to the risk associated with those peaches being contaminated. So we're seeing adjacent land use being pointed out more and more as a risk factor for produce production. Again, in this case, both the onions we saw previously and the peaches we're seeing here were not on those previous tables. So we are seeing more unique or never previously identified types of produce being linked to Salmonella outbreaks. After that 2020 onion outbreak, there was another onion outbreak in the US in 2021, where we saw 1,040 people sick from Salmonella or Reinenberg, again linked to onions, in that case produced and imported from Mexico. So a bunch of new outbreaks continue to happen all the time. A bunch of different microorganisms of concern to worry about. The outbreaks I talked about were linked to bacterial pathogens and viruses, Salmonella, the different types of Shiga toxigenic E. coli are the two we see most often. Listeria, also something we can see in different cases. I also talked about a hepatitis A virus outbreak, something that is certainly gathering a lot of attention and interest right now within the United States are outbreaks related to Cyclospora cayetanensis linked to produce, and again, primarily leafy greens at this point. But we do need to worry about all these different types of microorganisms on our product. So again, there are Codex Alimentarius standards for hygienic practice for fresh fruits and vegetables. They are old, adopted in 2003, and then annexes for different groups of fresh fruits and vegetables through 2017. GEMRA currently has a working group working to update some of the risk assessments associated with these different products. How to do useful testing for safety management in these products is in Book 8 that you've heard both Pete and Kieran speak about. Vegetables and vegetable products are covered in chapter 12, and fruits and fruit products are covered in 13. Both of these products cover both the fresh vegetables as well as the processed forms of these vegetables. Again, they highlight the different types of testing that we've heard about yesterday and today, looking at routine verification, environmental, investigational, and shelf life. For many fresh fruits and vegetables, we do a lot of environmental sampling, and that's some of the sampling I'll highlight as we move forward through the rest of this talk. Again, bunch of different vegetable and fruit products covered, both fresh and fresh cut that I'm focusing on here, but there is also an emphasis on cooked, frozen, canned, dried, fermented, sprouted seeds, as I mentioned earlier, preserved, specifically calling out tomato products. So both primary production and further processing is covered in all of these different chapters. So if you are looking for information on them, I would encourage you into these chapters. It's important to note that when we talk about fresh fruits and vegetables or produce, we are really covering a huge range of foods and food products, and different types of production, harvesting, packing, and processing strategies. And those strategies are going to vary both within a country and within regions through to other countries. And really, they're highly variable. So any recommendations given really need to be adapted to cover the specific or to the situation of the specific fruit and vegetables being considered, for their different cultivation techniques, their different harvest techniques, their different distribution, different processing, and different end uses. We do, have a huge variety of different processes we're handling here. We're going to talk a little bit now about primary production. So what to look for and what to sample for in a primary production environment. Primary production being that growth out in the field. For fresh fruits and vegetables, again, the ones we're consuming raw without any further processing. Really, prevention within this production environment is where we need to highlight our needs or our food safety inputs. When we discuss sources of contamination within the production environment, we sort of typically land on these 5 different areas, inputting risks into the situation. Talk first about humans, both used for harvesting the product and also used in planting and different production practices. We can talk about the soil itself, and if the soil itself is a risk factor in contributing pathogens into the product. Water is one that we'll highlight a lot on. Water is one that we saw highlighted in a bunch of those outbreaks I talked about. Building equipment and tools, these are our basic GMPs, and in a lot of produce production and packing, we have a lot of surfaces that are challenging to clean and sanitize, and environments that are challenging to keep clean and sanitized. And then, of course, animal intrusion, both wild and domestic animal intrusion, is a problem or a thing to consider. Again, talking about types of testing in that production environment, we know that our contaminants and how many we have on our product are going to be strongly influenced by our primary production practices and conclusions, and what different activities folks are taking there. Verification can be really beneficial for high-risk products, but not for all products. So something like a leafy green in the United States is commonly pre-harvest tested, same with sprouts that have sort of a different testing technique. But at primary production, the focus of our verification testing really usually focuses on our water sources, as well as our soil amendments or any types of soil amendments or fertilizer we're putting onto the water. And then as well as investigational sampling that we might do following a situation. So one of the main things we want to focus on is agricultural water. And there's a bunch of different types of water used in primary production of fruits and vegetables. So when we're looking at water, we typically want to ask ourselves some questions and focus on how much it inputs to risk. Surface water would be a higher risk than, say, groundwater. Also, our application method, is it contacting the crops that we're going to eat or the harvestable crops that will be harvested, or does it not contact the harvestable crop at all? And then we want to also ask ourselves a question about the timing of application and how close we're applying the water. And again, when we look at water, if you're using treated water or rainwater that is just falling from the sky, it tends to be a lot lower risk. Whereas when we look at surface water, and especially improperly treated wastewater or surface water that's got a tremendous amount of runoff from different risky environments into it, that would be our higher risk type of water. So we want to sort of understand where our water is coming from. And then again, our method of irrigation, again, are we applying it in a way where it directly contacts the produce in some sort of an overhead irrigation? Are we using it in a way where there's a lot of potential to splash onto product? Or are we using it as sort of in a more intensive agricultural way, where we've got something like a drip irrigation line with very low potential contact onto the fresh fruits or vegetables themselves, or something like a microjet sprinkler system underneath an orchard that would really limit contact with fruits or vegetables. So when we look into the chapter, again, importance of testing is gonna, be here based on our irrigation water and if our product we're producing is ready to eat, so going straight to the fresh market, or non-ready to eat, going through some processing. And again, if it's being used for pesticides or cleaning, again, in a way that's gonna contact food or the food itself or the food contact surfaces. We tend to test for an indicator organism, and in this case, we test for E. coli as an indicator of potential fecal contamination. And then again, would recommend, the sampling criteria here. You'll see that within our foliar applications or our pesticide applications and our cleaning products, especially for our food contact surfaces, we really are recommending absence in 100 ml of water, which is quite reasonable. Soil amendments are another thing to look at, and this is where we're taking primarily animal or human animal manure or human waste and putting it out onto the field. And these can be these again are known sources of our foodborne pathogens. And again, we need to consider both where the manure piles are being stored, and then how they're being applied, and how much work they're doing to reduce aerosolization and dust formation, and how close to timing or how close to harvest they're actually applying these different manures. Two different manure piles here at the bottom. We've got these are biosolids, so that's treated human waste in an avocado grove. And then this is a large pile of horse manure, which you can't see is on the other side of this. It's actually the water here is running off into the irrigation canal on the other side. So that would be a problem. When we look at those composted manures, again, importance of testing here is high. Generally can recommend testing for both indicator, E. coli, and different pathogens can be tested, again, at the different levels here. And again, you're looking at absence in 10 grams of manures going on to both vegetables, eaten raw, so composted, and pasteurized manures. In this case, we also see vegetables not likely to be eaten raw. And again, we can see very similar criteria. But in this case, where the vegetables are not eaten raw, the importance of testing becomes much lower. And if you've got pasteurized manures going on to vegetables not eaten raw, we again don't recommend routine testing, just periodic testing to verify effectiveness of that pasteurization. In this case, composted manures would be compost that's been stored and turned and heat treated, whereas a pasteurized manure would be something like a poultry pellet that's been treated thermally much more rigorously. And we go really quickly into the fresh cut fruits and vegetables. A little bit of a different scenario because we do have a lot more processing involved here. Again, our fresh cut fruits and vegetables are generally capable of supporting the growth of our bacterial pathogens and long-term survival. The important point I want to point out here is that Enterobacteriaceae coliforms and fecal coliforms are the normal part of flora found on all fresh fruits and vegetables, and they won't necessarily, well, they will not at all reflect the sanitary status of raw produce. So you should not be basing any testing around coliform presence on fresh produce. They will always be there. Again, if we're looking at fresh cut, again, when we look at importance, we want to look at our in process here very much. So not micro testing, but verifying that we have wash antimicrobials present in wash and plume water to control cross contamination. And I will say that within the processing environment, our environmental monitoring programs are increasing in importance as we continue to see more outbreaks. But again, we don't typically recommend testing of raw product or testing for shelf life. And then again here, if you are going to test end products, again, we don't recommend it, but periodic testing may be useful. Again, here, case 6 for our indicator organism would be generic E. coli would be the one we would recommend most frequently, and then followed by really low priority testing for our different pathogens with our different sampling plans, as is seen there. And this is just the same thing. End product testing of fresh cut fruit, we see the same sort of thing. Difference that we do highlight, although both low, between fruit that can grow Listeria monocytogenes and fruit that cannot support the growth. So that'll just be depending on what you fresh cut. So what conclusion, I just want to say that microbial testing is an integral part of our food safety programs, but it needs to be used appropriately and pragmatically. And that is going to be very focused on testing the inputs into our agricultural production systems. And then, of course, you want to continue to use the most current criteria developed by either expert elicitation or as required within your country's regulations. And it will they likely will vary depending on production practice, commodity, and end use. And then just to highlight again that many of our common indicators and other food products, Enterobacteriaceae coliforms and fecal coliforms, are not a good indicator within fresh produce, because again, they are commonly found as part of the normal microbiota on these different items. And so with that, Bernadette, I will turn it back over to you.
Okay, Michelle, thank you very much for your very nice presentation, very nice pictures, interesting pictures. And now I pass on to John Donaghy. John Donaghy is a corporate food safety microbiologist at Nestlé in Switzerland, where he deals with operational aspects of food safety. He is member of Icmsf since 2015. So John, I pass the floor to you. Thank you.
Thank you very much, Bernadette, and good morning, or maybe it's good afternoon for everyone there by now. And I will continue the theme that my colleagues, Michelle, Kieran, and Pete have started, and that's looking at a slightly different commodity. In my case, I'm looking at the dairy commodity and looking at the application of food safety management principles as well as microbiological criteria to this particular group of products. So again, I will start like my colleagues have done and give a plug for the ICMS books that we have produced over the years, and in particular book 8, which I think has been alluded to by Pete, Kieran, and Michelle, which really where it gives these guidelines or recommendations for microbiological criteria along the value chain of various commodities, from critical ingredients through to finished products. And the dairy chapter there is chapter 23 of book 8. But also important, and I think it's important for all of these commodities that we talk about, and Michelle and Kieran and Pete have alluded to this, is it's understanding the microbial ecology of the particular commodity that you're dealing with. And it's interesting what Michelle has just said, that sometimes are hygiene indicators because they're a natural microflora of some of the fresh fruits and vegetables, then they actually do not act as a good microbial indicator when we're thinking of sort of sanitary conditions of these products. So that's why it's important to understand microbial ecology of these products. And chapter 23 of book 6 actually does a comprehensive review of microbial ecology of dairy and dairy-related products. But it's not just the Icmsf that are writing about dairy and dairy products. You can see in on my slide there is a number of other really good reviews that have been done, including the Encyclopedia of Dairy Science, which is produced quite recently about microorganisms in milk powders. You have the Journal of Dairy Science. You have some other comprehensive reviews talking about sort of even the history of right through of milk and its uses, and the introduction of pasteurization and other processing technologies that have helped to improve the quality and safety of milk and dairy products over the years. So this is a sort of a recommendation for anybody who wants some light bedtime reading about dairy and dairy products, and beyond Icmsf and including Icmsf. So what we'll actually talk about today, well, my talk will really be divided in sort of these four sections. Firstly, I'll talk a little bit about the diversity in dairy products, because it's important to understand, and I think, as you've heard from Kieran and Michelle in particular, the diversity of some of these might be, you might think, oh, fresh fruit and vegetables, or I might think meat, but really when you actually dive a little bit deeper, you realize this can be a very extensive commodity base. And products thereof, and derivatives thereof as well. So I'll talk a little bit about that complexity. Then I'll talk a little bit about something which maybe we've not mentioned before, today anyway. And this is around the real drivers of food safety and quality in our food safety management systems. And it's about HACCP, and I call HACCP the cornerstone of food safety, and prerequisites, and particularly related to dairy products. And then I'll talk a little bit about microbial ecology, like my colleagues have done, around milk and dairy products. And then I'll take you through 3 examples of how we go about setting microbiological criteria for finished products, and then upstream through our environmental monitoring, through our critical ingredients, etc., for those 3 particular commodities, to give an idea of what organisms and perhaps what limits should be set. But also I'll look a little bit at let's say what has been applied in regulations in relation to some of these 3 products that I will select. So I give you this slide, and again, it's a little bit of a plug for my organization, you might say, and some of the products we produce, but I think it demonstrates maybe the complexity of the dairy and dairy type products that we actually have. And if I look on the left-hand side of your screen, you will see products such as UHT type products, like the coffee mates. And these are produced a bit like what Pete had said earlier. These are sort of products that have at least an F03 applied, and maybe even more. And so they will be defined as commercially sterile products. So the microbiological specifications that will be included in these sort of products for specifications at supplier level will mostly be around, spoilage type organisms that could lead to spoilage afterwards, because your processing conditions, your UHT processing, will kill all of your vegetative organisms, but you may have some spore formers surviving and end up causing spoilage, which can also lead to dissatisfied consumers and a sort of spoilage products and defects in quality. And as Peter said, the verification that's used in these sort of types of products is probably very different compared to some other products, because here we're talking about destructive and non-destructive testing, in terms of pH measurements, direct streaking, or even sort of incubating at high temperature or at different temperatures for a period of time to see if you actually get like quality defects. So slightly different from the other products. If I go on my right-hand side, I have something like ice cream, and this is a product which is, the finished product is a frozen product, which, so when we talk about listeria, this is important. It's a product that is made in factories that may conduct wet cleaning or controlled wet cleaning, so you still have some risk of listeria, and then that will dictate what we do. We also might have ice cream that will have added inclusions, and that also dictates what specifications you might set for your supplier, what sort of in process and what sort of environmental monitoring you will have, and even finished product testing. And then I go to the product right in the middle, and this is something like an infant formula, and or the peptamine beside it, which is again a powder product that is designed for special medical purposes. So these are products that are designed for a very sensitive consumer group, primarily those under 6 months of age. And when we go to this, they're not a sterile product, but they have to be safe for consumption, obviously. And then you have to think which organisms of concern. And again, here we add in Chronobacter, which is an identified significant hazardous microbiological hazard for this group of consumer. So you see, even though I talk about dairy in general, even across the range of products, you can go from something like a UHT beverage, to an ice cream or frozen product, or you can go to a powdered infant formula. So the nature of the microbiological criteria and the nature of the specifications you would set for ingredients of these, you can vary quite considerably. So that's why it's something it is important to actually, and with my 3 examples I will give you, hopefully indicate that variation. Although quite similar organisms in some cases, sometimes the limits change and sometimes the sampling plans change. I always like to take people back, since we are the Icmsf, and this is an Icmsf webinar, and in a simplistic form, I like to show this. No matter what dairy product we're trying to produce, or for that matter, any product we're trying to produce, we're trying to get to the right-hand side to a product that we reduce any pathogens to an acceptable limit, and we don't have a deviation in quality. But we're starting off from, in a lot of cases, a raw agricultural product, like Michelle mentioned for her category in terms of leafy greens or vegetables, etc. But it's no different from if we're doing meat or we're doing milk. We start with the left-hand side, whereby we have to try to control the H0, that is the initial level of contamination. And we know some of these products, as a raw agricultural product, may have pathogens present. And then we have our processing environment. So this is the area, this is sort of the reduction step, so the sum of your reduction, but then you also have the opportunity for cross-contamination of your product thereafter, so you are below the food safety objective. So all of in producing any dairy product, you are really going, to a certain extent, from at the very, very most upstream, a raw milk product that is somehow processed and maybe further processed, derivatives obtained, and then you eventually make your final product. And so along those steps, there will be different opportunities for cross-contamination, perhaps, which we have to always consider in food safety management. And going back to that, as I mentioned at the beginning, going back to this cornerstone of our food safety management systems, it basically, at the heart of that, is your HACCP system, which is your preventative approach, for doing your hazard analysis and identifying either critical control points with critical limits, or identifying the necessary OPRPs that you need in your factory. But underpinning all of that, and which is extremely important. Pete mentioned failures in CCP or failures in HACCP, but quite often when we see some of the outbreak stories and we see some of the incidents, it is quite often failures in the PRP. So you see the green boxes along the bottom is where often the failures can take place in, or maybe at the top of the pyramid, food safety culture in organizations as well. So it's not just about HACCP, which is extremely, extremely important. It's also about getting your prerequisite programs correct. And one of those, in relation to microbiology and in relation to microbial testing, is your environmental monitoring programs, because this is a verification of your hygiene sanitary conditions. And it also acts as an early warning that you see a deviation in your sanitary conditions, like I think Bob mentioned yesterday in some of his examples of where you can get different ways of contamination. And then when we speak of microbiological criteria, really it is a verification. And it is actually, in some ways, verifying. It is not the guarantee of food safety if you comply with the regulation necessarily, but it means it is a verification that your controls are under your prerequisite programs and your HACCP system and your sanitary conditions are under control. So really the bottom of the pyramid is extremely important. And To that end, in respect to dairy, I point you to a few other documents about upstream good practice. And the International Dairy Federation, for example, has produced many documents in relation to this. And I think these are really worth, I'm not going to go into the detail here. Also, the Canadian Quality Milk on Farm Safety Programme, and also the likes of Dairy Australia have produced very good documents that really guide you on ensuring your H naught, let's say the start of the equation, the H naught is as low as possible. And this is through good milking practices, good cleaning practices, good water application practices, good storage, distribution, temperature control of your milk. All of these things play a really big role in terms of bringing that H naught down before you start any processing whatsoever. So in terms of the microorganisms that we see typically associated with dairy, and as I say, you might say dairy has them all, or a lot of them. So I think when you look at some outbreaks that have taken place over the years, you'll have seen some of these organisms popping up. Listeria in cheese is a common one. S-tech in cheese is a common one as well, particularly in raw cheeses. So if I look at some of the US figures, for example, in terms of outbreaks, you will see quite a few associated with listeria, quite a few associated with listeria in cheese, but also raw milk. Raw milk products. So if you have a raw milk product, you increase your chances of actually having some of these pathogens present. Some are a little bit more unique than others. As I say, cheese, listeria, and S-tech is quite common, along with Campylobacter. We've seen a few reports of foodborne cases, because generally you don't have large outbreaks with Campylobacter, but you've lots of sporadic cases, and you've seen some associated with cheeses and with raw milk as well. Butter and cream, it's a little bit the same culprits, let's say, with Staph aureus in there as well. You've seen Staph aureus also with some milk powders. I think people remember back to a couple of decades ago with the Snow brand in Japan, where there was a large outbreak related to Staph aureus enterotoxin as a result of a failure in the processing, and milk was stored inappropriately for a long period of time. You had Staph aureus growth, enterotoxin production, which was then not, destroyed through heating further down the chain. So again, milk powders, Staph aureus is one microbiological hazard. Salmonella, obviously. Chronobacter, obviously, for the infant formula and products of that nature. And then you have Bacillus cereus. I think someone asked a question about this yesterday. Bacillus cereus is one of these organisms which, again, can cause illness, can cause spoilage. Some strains, some of it can produce emetic toxins like cerulide, and so you have inappropriate storage conditions. You end up getting cerulide formation in products like cream, for example, if you have overstorage of emetic Bacillus cereus strains. Then, of course, there is some of the other ones where, in countries where you have things like Brucella, you have Mycobacterium bovis, tuberculosis, high prevalence in cattle, then these can actually be a risk for the raw milk as well and further processing of milk. And then there is always some, emerging hazards. And, we've heard about sort of Coxiella burnetii. We've also heard of Mycobacterium paratuberculosis, where there's been tentative links or causal effect relationship between, raw milk and Crohn's disease around Mycobacterium tuberculosis. But again, there's been a lot of studies done there, and, the link is not conclusive at this point in time. So just to, give you a quick roundup of many of the reviews that have been done, you can see quite a number of the, let's say, traditional microbiological hazards can be found and can be associated with raw milk. And obviously it's up to during the processing to reduce those to an acceptable limit. And then we come back a little bit to testing, and Michelle talked about some outbreaks or some foodborne cases. And just a case in point about microbiological specifications, not necessarily guaranteeing zero risk or guarantee, that all of the product produced, will not have the organism of concern in it, because we cannot test all of the product. And you've seen over the last couple of years, and just recently, you have seen a story relating to infant formula in France, where it was Salmonella, and more recently you've seen with infant formula and Chronobacter. And in both those cases, from all of the publicly available information, all of the finished product complied with the full specification in relation to salmonella, which is like 60 by 25 grams, and Chronobacter 30 by 10 grams. And I know certainly in our own infant formula manufacturing facilities, this is what every batch is released at this with that sort of specification. But of course, as mentioned before, it is also supported by extensive environmental monitoring, extensive auditing of suppliers, extensive stringent raw material specifications, zoning, cleaning, etc., etc. So it's not just about testing the finished product, because here are cases in point whereby you comply with the finished product specification, but yet in these sort of dairy products in very sensitive populations, you can get illnesses. And it goes back a little bit to a point that our colleague Bob Buchanan has mentioned before. Now we're in a situation with the likes of whole genome sequencing, whereby cases can be more easily linked, which maybe could not have been linked before. So, if we, with whole genome sequencing, I taken one case on the salmonella story, I think there was 38 cases across different countries. And somehow through the public health agencies, those were able to be linked because they were seen as the same sequence type of organism. The same in the Chronobacter situation as well. If all organisms isolated from the clinical case all are the same, then that immediately triggers an investigation. So, with tools like whole genome sequencing, we are probably seeing more foodborne cases and outbreaks now being able to be linked. So it questions, then what do we need to do with our finished product specifications, as a verification tool. And there is no doubt in terms of what are the right hazards for these sorts of products like infant formula. And we've seen over the years, that there are outbreak cases in relation to salmonella in infant formula, and also with Chronobacter on the right hand side. So, and I'll come back a little bit to discuss that as well. But when we talk about what's the relevant hazard, or what's the relevant microorganism to be included, for example, in finished product specifications, critical ingredients and environmental monitoring, you have to look at the history, and you have to look at sort of the organism that's associated with that particular product. So if the evidence is telling you that there's outbreaks associated with a particular commodity, and a particular pathogen, then that's where GEMRA and the rest have actually then sort of decided that, well, as a proper risk assessment, that it's advised those to be included in microbiological criteria. We see the same a little bit on some other commodities as well. Again, these are products which, in some cases you might say, argue that they're low risk with respect to, some of these pathogens, or you might say, well, they're high risk. And the Bluebell ice cream story, and again, everyone does not know the full details, but in there, those products were being fed to a vulnerable population. And in those cases, again, it's not knowing if the product was put in a situation where it supported growth, perhaps. It was that the situation, or was it patients who are more vulnerable to low levels of listeria, or there's a particular virulent strains of listeria that actually happened, in these factories? But of course, there is sort of a shortcomings probably in terms of manufacturing, in terms of the PRPs as well, because I think it was found in some of the products in the process environments. The same salmonella and cheese. So there is no doubt there is outbreaks associated with many different dairy products and different microorganisms. And here I just show you the salmonella, listeria, and Chronobacter, let's say, for infant formula. So, it is important that for these sort of, let's say, products, then these particular organisms do have to be controlled. And then I come back a little bit to this as a sort of a common slide. And what you see on the right-hand side is really a little bit what I showed at the very beginning, to show you the complexity of dairy and dairy products. And you could probably do this for meat. Kieran could have done it, or in the same way as Pete or Michelle could have done it for the fresh produce. But you see, you start at the very bottom, raw milk, and then you immediately start, there's a lot of raw milk products available, even raw milk cheeses, but then you can go through a heat process, and then you end up with pasteurized milk, and then you can end up with powder, and you end up with whey powder, non-whey powder, skimmed whey powder. And when you think, how do I set a specification for this? So if I'm a manufacturer and I am buying some of any of these boxes that you see here, then how do I set a microbiological specification to my supplier around this? Well, of course, I look at the points on my left-hand side, my 1 to 8, which are recognized principles for setting of microbiological criteria. And and this is always important when you think of even setting, as a manufacturer, setting specifications, or as a regulatory organization setting microbiological criteria for a product. You ask yourself always these questions: are the pathogens associated with the food or the ingredient? First question. Again, you go to literature, you see outbreaks, etc. in the past. Where is this sort of pathogen product association? Is there distinct associations? Are the ingredients likely to be contaminated? We see from Michelle's story and from even from Kieran's story, it depends. And there is water, there's humans, there is equipment, there is all different avenues of contaminating some of these products if they're agricultural products. Are there robust processing control measures, kill steps in place, reduction methods? And of course, this is where your HACCP study comes in as well. So even if you identify it, an organism as an intrinsic hazard, do I have control measures in place? How should I set critical limits for those, or are they a no PRP? Depending on how you do this in your HACCP assessment. Is there potential for recontamination from handling in the environment? A very, very important one, and it depends on your environment. Post-process environment, is there an opportunity for cross-contamination? I think Pete mentioned in the shelf-stable category, there generally your retorting or your UHT probably impact. So the chance of post-stress contamination is minimal, and so that's why environmental monitoring doesn't serve a great purpose. But if you're producing a milk powder after pasteurization, you're doing spray drying. So after your pasteurization, you don't really have any more kill step, but you have potential product exposure. Then it's important to consider what organisms should I monitor in my environmental monitoring program. So it's my in-process controls, but also my environmental monitoring. Does my product support growth or survival? This also is extremely important, and certainly when at the session tomorrow in Listeria, this is a critical step. And with regards to the microbiological criteria you can set for Listeria, is it a growth or a no growth product? And then is a product meant for a higher risk group? We have seen in the past, and particularly in relation to dairy, infant formula and follow-up formula, and products for special medical purposes, which are in a lot of cases dairy-based, or they have some dairy-based ingredients in them, then they are meant for a high-risk population. So again, this has an important bearing on setting of microbiological specifications at your supplier, or what you set for your finished product. And then the shelf life of the product, and then that consumer handling and use. Will it increase, decrease, or the level of the pathogen, if it's there, remain the same? And I think Leon mentioned this yesterday as well around Chronobacter in particular, because if there's mishandling of infant formula during dissolution, let's say, and storage, then this can actually lead to sort of an increase in, for example, Chronobacter in your product. So all of these 8 points are critically important when we're thinking about microbiological criteria and setting them. And as I say, this is what has to be considered when, as a manufacturer, we're thinking about ingredients, or if we're thinking about finished product specifications or in criteria, particularly if none exists in the legislation. So in line with what everyone else has said before, going back to Book 8, really we divided up in terms of where and what microorganisms do we need at various steps. We really talk about the critical ingredients, and you saw this in the tables from Michelle, from Kieran, from Peter said, what do we need for critical ingredients? What in-process controls do we need? What do we need to monitor in our process environment? And what is recommended at end product? And this covers both food safety criteria, process hygiene criteria, and also utility organisms. And I would like to take you through now 3 examples, one for infant formula, one for ice cream, and one for pasteurized, what we call low water activity hard cheese. just to demonstrate how we establish and how we do this. So just to take you through very, very, very briefly, the manufacturing process for infant formula. It's really divided into, I call the wet and the dry process. So basically you will get your milk in at the front end, and this may be your raw milk direct from fresh milk, or it may be milk powder, which is then reconstituted depending on transport of the powder, and you get a standardization. But then you have your critical CCP, and this may be some form of thermal processing, direct steam injection, pasteurization, etc. Then we go through evaporation, and we end up then doing spray drying. This top part is very much I call it the wet processing environment. And it's really post that, and when we go into the spray drying area, is really where we're in a dry environment. And this is where organisms like Salmonella, Chronobacter can survive, because they can survive in dry environments and can survive in low moisture foods like infant formula. So when we think about let's say or what we will test for, then we really have to think about what do I do in terms of my in process. So in process we will be testing for, and I will show this in a minute, we will be testing for EB, Salmonella, Chronobacter, etc. But then also in depending on the manufacturer's choice, they may be adding many different what we call critical ingredients. And these are critical ingredients which actually will be added post the heat processing. So these will have to have the same microbiological specification to match the finished product specification. So if I'm buying a vitamin mix or trace element mixes and I'm adding them here, then these will have to conform with the same specification of my finished product, i.e. Salmonella N equals 60 times 25 grams, Chronobacter N equals 30 times 10 grams, and EB absence in 10 grams. So when you're adding critical ingredients that actually will not undergo your heat processing in your own manufacturing, it has to comply with the finished product specification, which is, as I say, written here on the side. It's called Enterobacter sakazaki, but really now it's Chronobacter species. And then when I mentioned earlier about microbiological criteria changing over time, and this infant formula is really a good example. You may recall in one of my earlier slides, I showed you outbreaks and foodborne cases related to Chronobacter and powdered infant formula. As that evidence started to build, they realized that powdered infant formula could be a source or a cause of Chronobacter illness in infants. And then a sort of a general study was done, and this was the early 2000s. And based on that, it was recommended that Enterobacter sakazaki, as it was known then, which is now Chronobacter species, should be added as a significant hazard, particularly for infants under 2 months of age and up to 6 months of age. So you see the criteria changes with availability of evidence. And here it really demonstrated well that in Codex, then the criteria was suggested as in 2008 with this N equals 30 absence in 10 or N equals 30 times 10 grams, absence of Chronobacter. So this is from then on. Then obviously all manufacturers were aligned with this, and Chronobacter became a relevant organism. So if I look, for example, infant formula today, what would we do? Again, looking at on the left-hand side, what everyone has shown you earlier this afternoon. You have critical ingredients, in process controls, process environment, and finished product. What would I test for? Okay, so this is typically if we are buying critical ingredients, so they will not get a heat treatment or a microbial kill step within the manufacturing facilities. They will have to meet the total plate count, the EB count, Salmonella, and Chronobacter. And I'll say other here as well, just bear with me a minute. Then in your process control, for example, maybe in some of the semi-finished product, you may also test for EB and Salmonella and Chronobacter as well. And certainly throughout your process environment and your product contact surfaces, you will be measuring EB as a hygiene indicator, as well as the relevant pathogens, which are Salmonella and Chronobacter. And when it comes to your finished product, you will have your total count to meet your full microbiological criteria. You'll have your total count, you'll have your Enterobacteriaceae, Salmonella, and Chronobacter. And depending on the regulation in your country, I don't know if I can't see it on my own screen, is a little bit blocked out. You will see in some countries you will also have other parameters there. For example, Bacillus cereus may be in some regulations, and I've seen this 3-class plan in some regulations with respect to Bacillus cereus. And in that case, when you are purchasing your raw materials, quite often you'll include things like Bacillus cereus, or perhaps Staph aureus, or mesophilic spores in general. Because this is you will have criteria set like this, or for other quality reasons you may include other organisms. And obviously, then if you have it in your legislation, for example, L mono. And this is, for example, like in the European legislation, you will then, do a monitoring program. Maybe not every single batch, but certainly as part of your monitoring program, you will do Listeria monocytogenes absence of 25 grams. So again, often, not every regulation is actually the same, but you certainly have to apply with this regulation. And if I look across Europe, for example, many of the different countries will actually do surveys quite regularly of infant formula and look for Listeria monocytogenes. I have not seen any reports of findings of L mono because it's a dry material. You might say it should not be vulnerable to Listeria monocytogenes, but nevertheless, it is there in the horizontal legislation in Europe. Then if I move now to something like ice cream, for example, and again, what does the process of ice cream look like? For maybe some people are a lot more familiar with ice cream than I am, but I only eat the stuff, so but we do manufacture it as well. But you see, you start for milk, for example. Again, you have a mixed tank. Generally, you have a pasteurization step, which is generally your CCP in the ice cream manufacturing, ice cream where milk is actually used, let's say. And so you have this is your sort of your key area, a bit like the infant formula. But then you move down to the cooler, the hardening tunnel, the freezer tunnel, and then you go to packaging. So this is the following process. Now, if I look at that, where is my microbiological risks, you might say? Well, obviously, if I'm looking post-pasteurization, then of course, I may be adding inclusions to my ice cream. If I look at my pretty picture on the left, I may have chocolate chips, I may have raisins, I may have nuts, etc. These are what we call a dry mix ingredient. These actually, you can also represent a risk for salmonella. So are they processed by the upstream supplier? Are they not processed? Do we have to process? Do they meet the finished product specification? Remember, we could actually pasteurize our milk, but then we add something that actually introduces a microbial risk, like an inclusion. So we have to be able to manage that as what we call a dry mix or a dry mix environment. So if we are storing somewhere where we have nuts, for example, that will be managed very much as a dry mix environment. It will always be dry cleaned, and we will monitor for EB and salmonella. Whereas if I'm looking at my area here around my freezer, for example, then we have some very vulnerable areas to Listeria contamination. For example, anyone who's in chilled frozen business will know, entrance points and exit points from freezers are vulnerable to Listeria because you get a differential in temperature going from ambient to freezer. And at the exit and entrance points, you get condensation and you can get Listeria, harbor spots or condensation. And so you can have vulnerability to Listeria. So again, in these areas, we'll be thinking about Listeria species. And if we have deviations in Listeria species as a hygiene indicator for Listeria, we may also then look for Listeria monocytogenes and even include Listeria monocytogenes in our finished product microbiological criteria. So again, you see it depends on the ingredients you're using, not necessarily the main ingredient, but even inclusions. And it depends on your process, and it depends how you manage that process in terms of the zoning, the cleaning, etc., and what organisms are of concern in your environment, in your ingredient, and what you should test for in your finished product. So again, you see on the right-hand side what is given in our Icmsf chapter around ice cream, for example, and you will see in finished product testing critically, they call out Salmonella and Enterobacteriaceae as your process hygiene indicator, with case 2 for the Enterobacteriaceae and case 11 for Salmonella. And this is a little bit typically what we would do in ice cream factories. So ingredients, critical ingredients, high importance, EB, Salmonella, and possibly Listeria, depending on the ingredient that you may be adding. If I'm adding, for example, Icmsf strawberries or raspberries, these are vulnerable to Listeria. These are an agricultural product, which depending on how they're treated upstream, depending on how they're frozen, they could introduce Listeria. So this is what you have to decide. Whereas if I'm buying, for example, chocolate chips, Listeria may not be important, but my Salmonella is important as a critical ingredient. If I looked at in process, okay, you might do some hygiene indicators along your process. You might have all those other process controls, obviously around your pasteurization. Obviously, will be a critical limit, but you'll have some other process controls along the way as well. Your process environment, as I say, Listeria species, as I talked about in my wet cleaned areas, but also in my dry cleaned areas, for example, or my controlled wet clean areas, I will certainly have EB as an indicator of my process hygiene. And Salmonella may also be included there as well. These things are not necessarily in stone, but these are indications of what we would typically do. And then in your finished product, as I say, you certainly will have your EB, like we recommend in Icmsf. We will have Salmonella, and most likely we'll do some form of monitoring for Listeria. And if we go to the likes of our legislation, if I go to somewhere like Europe, you'll see in Europe, you have the horizontal legislation, all ready to eat foods, unable to support the growth of Listeria monocytogenes. So this will be like an ice cream. Then you would have an N equals 5, with a limit up to 100 CFU per gram, because it's a frozen product, it's a non-ready to eat. So this is a horizontal legislation. So that's why we would include in finished product criteria of our products, we would include Listeria, because obviously it's clearly in a lot of legislation, let's say cross-category legislation. Ice cream as well, you will see the Salmonella similar to what is in our Icmsf recommendation, for absence 25 grams. I think here it calls out 5, N equals 5. Icmsf, we called out N equals 10. For the process hygiene indicator, again, you see this is the same as what was recommended in Icmsf. It's a 3-class plan, N equals 5, C equals 2, and small m 10, large m 100. So again, the European legislation looks very similar to what we see in Icmsf, apart from the fact that we do see Listeria here as a horizontal for ready-to-eat foods. And we don't actually call that out specifically in the Icmsf table. But as we've said often before, the Icmsf tables are guidelines, and there will be variations across the legislation. And just to prove that point, or well, it's not proof, it probably proves that to a certain extent there is similarities between many of the different regulations. This is the Food Safety Code for Australia, for example. Again, what does it call out? Listeria, same criterion. This is sort of a bit of a plug for the Listeria talk tomorrow. It even sets out the criteria for what is a growth, no growth food. And obviously ice cream falls in a no growth food. So again, you'll have a limit of 100 CFU per gram. But also even parts of Australia, Dairy Food Safety in Victoria, Australia, calls out Salmonella, Listeria again. So they're both pathogens, but it calls out E. coli as a process hygiene indicator as opposed to Enterobacteriaceae. And this is sometimes what we see across different regulations across the world, particularly around process hygiene indicators. Sometimes we see Enterobacteriaceae, sometimes E. coli, sometimes coliforms. So that varies by regulation. And here's an example, even for ice cream in the Food Safety Code. So if I look at cheese, for example, again, I show a similar sort of pattern. Again, what do we do? And it depends. This is hard cheese, remember? So I don't have a diagram of cheese making, but hopefully most of the audience will understand how cheese, like something like cheddar cheese or Gouda or whatever is made. So you have a sort of an acidification, and then you have a sort of a coagulation, and then you have a ripening period, let's say, and a maturing of your cheese. In a lot of cases. So again, it's a sort of a dynamic biochemical process of fermentation, you might say, cheese making. So again, that can also dictate the organisms, but generally you'll have hygiene indicators, for example, EB, utility organisms there as well. Salmonella for some of the ingredients. Again, many cheeses don't come as cheese. They also have inclusions. Some of these inclusions, if you're not careful, can add to the risk. So if you're adding spices and herbs and etc., perhaps to your cheese, then you have to be careful that you're not introducing salmonella with those. So again, the critical ingredients specifications for your supplier has to match what you have in your finished product. In process control, a lot of it is around about controlling your fermentation, let's say. So as your pH control, your titratable acidity, etc., maybe your water activity of your cheese, etc. So all of these are very, very important, as is the likes of Staph aureus, because again, we know there has been instances of either enterotoxin, foodborne illnesses relating to cheese. So Staph aureus is another important pathogen in cheese. And the limit will depend on where you want to take the sample, either before ripening, at the end of ripening, because in some cases the levels can actually decrease over ripening. So you could have had growth or contamination at an early part of cheese making. You get enterotoxin production and the enterotoxin remains, but the Staph aureus viable cells perhaps have disappeared during ripening, and then you would miss that. So again, it has to be important of at what stage in the cheese making process you maybe monitor for some of these parameters. And again, finished product, we look at salmonella, again, listeria, because in some of these you have salting and brining tanks, and these brining tanks are very vulnerable to listeria contamination, and then you have coatings of cheese as well. So rinds that are put on cheese, some of these tanks sit for a long time. They can support the growth of listeria. So it is extremely important in some of these cheese making process as well, and important to monitor and to be important as part of your criteria. And again, just this is a reflection again, the EU, you look at the European Union, the types of criteria that will be set. Again, we see listeria, as a sort of the horizontal specification. We also see Staph aureus. So what is in the ICMS table? It talks about salmonella, it talks about listeria, it talks about E. coli, it talks about Staph aureus as being relevant pathogens, and at various stages and various limits that we can set further criteria. And this is very much reflective of what we see, for example, here in the EU regulations. We see listeria, we see Staph aureus, either Staph aureus, coagulase positive Staph aureus, or we see even the enterotoxin. So depending on when you want to actually analyze and the type of cheese manufacturing process you have. And here you also see E. coli in as a process hygiene indicator for some of these cheeses as well within the European regulations. Again, here you will see I've just called out European Union, I've called out Food Safety Code Australia, but honestly, I could pick any regulation in the world. And when I've done this before across dairy products, you see very similar, be it India, be it Australia, be it Canada, be it European Union, generally the same organisms there in terms of your food safety criteria. And in terms of your process hygiene indicators, you might have some variation, as I mentioned before, depending on E. coli, depending on whether it's Staph aureus or perhaps it's coliforms. So you see perhaps subtle differences, but in the main, the organisms are the same. And you can have some maybe slight differences in the limits that are set. But as I keep saying, and I think other people have said before, is the ICMSF acts as a really good guideline for what to set. So just to conclude, and my final slide, I think it's been said by Michelle, said by Pete and Kieran, product testing, is very useful, but it can have limitations. We don't test safety into products. No matter how much testing we do, unless we test the whole thing, the whole product, and if nothing left, it's the only way to guarantee safety by testing. That is not what testing is about. It's about verification of your processes. HACCP is key, and your prerequisite programs as a supplement, to testing. Also focus on process control. This is extremely important. I mentioned on some of the dairy products, be it yogurt making, cheese making, etc., or commercial sterility. Process control is ultimately extremely important. in products which are not commercial sterile, then you look at your environmental monitoring programs and what organisms, suitable organisms that should be there, be it Salmonella and EB in dry environments, Listeria species, and subsequently L. Listeria monocytogenes if you're in a wet processing environment. And again, it's applying proper root cause when you do have deviations, that you actually have the proper tools. And here's why I talk something about whole genome sequencing is one appropriate tool when you want to do good, sustainable root cause analysis. And this is appropriate not just for dairy, but for any sort of manufacturing. So that is it from my side. And thanks very much. So I know I'm the last person. There may not be questions, but happy to take questions and happy to hand back to you, Bernadette.
Okay, John, thank you very much. Now I pass over to Michelle. She will manage the questions that we have received. There are a few very interesting ones. Unfortunately, we have only 10 minutes or 12 minutes to finish, but I think we can discuss some important points. Michelle, please.
Perfect. Thank you, Bernadette. John, can you stop sharing your screen so we can get everybody on the
okay, sorry.
Yep, no worries. And when we get everybody up here, Pete, I'm going to start with a question that came in towards you. And it is it common to set a shelf life for shelf-stable foods while in sealed packaging? And then it says it's done in my country. And the question is out of Brazil.
Right. Thanks, Michelle. Yeah, it is quite common to set shelf life. Usually it's labeled as a best before date in many countries. And the best before date is on a can. It's on the bottom of the can, stamped in lettering on the bottom of the can. So it will be somewhere on the packaging. And depending on the packaging type, usually it's going to be between 12 months and 36 months. So between a year and 3 years. Most commonly, it's 2 years. So that's the most common shelf life best before date that you'll see on packaging. And it's purely for quality reasons, not for safety.
Thank you. Thanks, Pete. Kieran, the next question I have is for you. Why is routine testing for Salmonella not recommended for raw commuted meat?
Thanks, Michelle. Generally, Icmsf doesn't recommend testing for raw meat products or raw comminuted meat products because several countries and regions, they have established performance objectives and performance criteria at a certain step, either at the farm or at the plant. And generally, as we have seen yesterday also, this approach, Wayne's presentation showed for Campylobacter in poultry, this approach has been accepted at many places, but there are variations in Salmonella in different regions and different countries, and Icmsf recommendations are only guidelines. And depending on situation, as John has just now shown in his slide, the microbiological criteria setting. So depending on the process controls, cooking, and all other cross-contamination, everything, one can have their own micro criteria set for the organism.
Perfect. Thanks, Kieran. Pete, I'm going to go back to you. And the next question for you is, in the case of shelf-stable foods, do the Icmsf sampling plans recommended for case 15 apply to them?
Short answer is no, Michelle. So no, the case 15 really is for Salmonella pathogens and high-risk foods. So for ambient stable heat-treated foods, we don't recommend routine testing. What John referred to this earlier. What you might need to do in some cases is some countries have legislation set for thermophiles in canned foods, and they will specify the test you need to do. Commonly, that's incubation at 55 for the packs for 7 days, and then you determine whether you've got any spoilage. That's really the only common thing that's applied and that you might need to do. If you have a problem and you need to do investigational sampling, then you would choose whatever sampling plan case plan is relevant, and you would often do that to determine if there's a time during manufacturing when something went wrong and maybe link it to an event, or to determine the defect rate, because defect rate is important for assessing the risk the product to consumers. And the company manufacturing should want to know that, and the people investigating if there is an outbreak will want to know that as well. It's important for risk assessment. So it's difficult to define a case plan that's relevant and really is up to the particular situation.
Perfect, thank you. So this next question is going out to everyone on the panel, and it's a bit interesting. Denmark is currently investing in the development of a climate label. In the first phase, they're putting in 1.2 million euros, and it's a state-controlled label regarding to climate. Could a smart label for microbiology be developed along the same line of reasoning? John, do you want to start that?
Yeah, interesting concept, because many people have talked about this before. How do you advertise, let's say, safety? How do you sell? Can you sell food safety? But I suppose it's food safety is always viewed as a given. That's as WHO always says, if it's not safe, it's not food. There's many discussions around this with marketing people and the likes of whether this will be a way to go. I can't see it catching on quickly, but certainly I've seen these claims coming around, certainly around sustainability and around other topics. So certainly it is going there to emphasize that manufacturers are going a certain direction, particularly on the sustainability front. But I think consumers would still expect products, to be safe, without having a label to verify that or claim that.
Peter, do you want to follow up on that at all?
Yeah, I'm just wondering if the question is more. Is the question more to do with an indication of microbiological quality based on something sensitive in the label in the packaging? Rather, depends on whether the question is related to, is the climate sensitivity label intending to reflect the climate that the product has been through? I'm not quite.
Yeah, that's a great question. I don't.
Yeah, I don't know either. That's another angle as well. So yeah, of course.
Yeah. And there have been
some a smart sensor, right, that would indicate if something's grown in there.
Yeah, and there have been some good, interesting research projects, but nothing that I've seen that's really been effective in that respect.
Kieran, do you want to add anything else to that discussion? No. Okay. So the last question I've got that's come in so far has to do with artificial intelligence. And do we think that there is a place for artificial intelligence amongst microbiological testing of different commodities? And can it help, or will it do any good? And I'm going to start with John on that, because I know big data is one of his favorite topics to talk about.
No, I think, as I talked about yesterday, I think, the more, there is now a lot more data being captured around food safety and quality, I say, along the whole value chain. And I think if it can be somehow made interoperable, that one bit can speak to the next bit, to form some sort of prediction, I think it will be useful. But from all of the artificial intelligence tools that I have seen, it requires a lot of an iterative approach, to make sure that you go back in the loop, so that it gets better and better, and the more and more it learns, the better it is. So I wouldn't, say it's a no-go. I would say yes, it is certainly worth a trial, and I've seen many sort of projects on it, and some of them look very, very interesting. So I think, but again, it's down to, as I mentioned maybe in my talk yesterday, is about the veracity of the data. What goes into the data, what continues to feed into it, and then verifying that the results are okay. You will still need to say, I'm afraid, people like us, so-called experts, to still look at the what the output is and not use it blindly. That's always my fear with things like machine learning and artificial intelligence, that we move away from expert elicitation and that people will use some of these things blindly. That's my caution against it.
Karen, what about you? Do you have any thoughts about artificial intelligence being used in the future of microtesting?
I agree with John, what John has said. The quality of data and the process in which the machine learning thing happens, then only it will be very useful. And a lot of studies and a lot of things are going on in this direction. And maybe in future we may have some kind of thing which will be helpful for us in food safety.
Perfect. And Peter, over to you.
Yeah, I think in terms that one more obvious area I think where it would apply would be in process control, where you have automatic or automated measurement systems, and it may be easier to capture that data and use it. But also on the point of microtesting, whether that's raw materials or in the environment or finished product, then I think the metadata are so important in terms of how you interpret that, and making sure you have all the relevant metadata there for every test you do can be, I can imagine that's going to take some effort to do. So as long as you can get all the metadata, then I think that it would offer a lot of promise. Yes.
Yeah, I would agree with that. I would argue, though, that it's not just getting the metadata, it's getting the metadata in a tidy format that's useful by the AI tools. I know, formatting of the data is a huge issue with a lot of micro data as well, and especially with metadata associated with it. There's been a follow-up question to that. What about using AI for monitoring outbreaks? Any thoughts on AI for monitoring outbreaks?
I suppose it's a possibility, but you have a lot of good tools now that add visual, like say visual dashboards to looking at outbreaks. I mentioned maybe yesterday that you will see there are many commercial tools now as part of early warning, and to a certain extent they're using AI to try to make predictions of where is going to be the next high risk material, be it from fraud, be it allergen risk, be it salmonella, or be it listeria, based on retrospective data. So these tools, these commercial tools that are available, are actually using algorithms and AI algorithms to try to predict let's say where there is some outbreaks. I remember looking at one, just to mention one by name, is the ethylene oxide, where the ethylene oxide story in Europe in particular. And in that, probably 1 or 2 years, about 1 year beforehand, some of these tools that I saw were talking about ethylene oxide in some herbs and spices, that there was some findings or whatever, and it was sort of predicting that, this could be the next thing. Now, you don't know, is that what triggered people to start to look more, or was it that they were getting the trigger correct? So this is a little bit, was it the algorithm working well, or was it the fact that this alert was made that people start to look more? But, certainly I think some of these commercial programs now are looking in this direction by looking retrospectively at all of the data globally, because that's sometimes the difficulty, and it's for us, like say, as a global manufacturer, it's important to capture data globally. You're not just operating in one country, you're not just buying ingredients in one country. So, maybe having that big data from many different global sources, where your food is sourced from, that could help you highlight some things that you may normally not be aware of if you're just where your manufacturing site is. So, I think there are people using that currently, to try to predict what's the next big thing. But again, it's only as good as the algorithms and as good as the data that they collect and can access.
Anyone else want to weigh in on that? All right. Well, Bernadette, I'm going to turn it back over to you because we are at time.
Okay, so we are right on time to finish. I thank everybody for following us, and I also thank the presenters with this brilliant and overwhelming amount of information. And I hope to see everybody tomorrow again. Tomorrow we will have an interactive section, so people that have registered to the meeting, to the webinar, we have a password, I think, to connect Zoom tomorrow. And so I'm happy to meet everybody again tomorrow. Bye-bye. Have a good rest.
Thank you very much, Bernadette. Thank you, everyone.
Thank you.
Thank you.